Hello there, and welcome to Science for Sleep, where curiosity gets cozy, distant worlds drift a little closer, and the universe takes its time so that you may rest. Tonight, our gentle journey leads us toward a planet so unusual that it sounds less like astronomy and more like something invented by an overenthusiastic jeweler with access to volcanoes. Its name is 55 Cancri E, a real world orbiting a distant star, often described as a diamond planet, and a place where lava may move like oceans beneath a sky no traveller would wish to breathe. Some planets invite easy imagination. We picture blue skies, rocky mountains, rings of ice, perhaps clouds crossing a familiar horizon. This one resists comfort. It glows with heat. It circles its star at remarkable speed. Its surface may be reshaped again and again by molten stone. Even its nickname, sparkling and glamorous as it sounds, hides a far harsher reality. If you were somehow able to stand there, which I strongly advise against, you would not admire gemstones for long. You would become part of a very brief cautionary tale. Still, there is something irresistible about such places. Perhaps it is because worlds like this remind us that nature has no obligation to match our expectations. We grow up thinking of planets as categories. Rocky planets here, gas giants there, icy bodies farther out. Then the cosmos quietly produces something that seems to have been designed by a mischievous physicist. A superheated world larger than Earth, packed tightly, rushing around its star in less than a day. Possibly rich in carbon, maybe wrapped in vaporized rock, maybe gleaming in ways we're only beginning to understand. Before we settle into this voyage, I would love to know where in the world you're listening from tonight, and what time it is in your corner of the Earth. Perhaps it is late evening. Perhaps dawn is still deciding whether to arrive. Perhaps rain is tapping softly at a window, or perhaps the room is still and warm and ready for sleep. Wherever you are, I am glad you're here. If you find this little expedition soothing, interesting, or simply a pleasant way to unwind after a long day, I would be grateful if you gave the video a like and maybe subscribed. It helps this quiet corner of science reach other tired minds who would enjoy drifting off while learning about impossible planets. Now, get comfortable. Let your shoulders loosen. Let the day step back a little. There is no hurry where we're going. We are travelling many light years away, and the universe does not mind if we arrive slowly. Our destination lies in the constellation of Cancer, the Crab, though no crab has ever looked less relevant to the matter at hand. Around a star known as 55 Cancri, astronomers have found a family of planets. Among them is the most famous sibling 55 Cancri E, a world that has captured imaginations because it seems to combine treasure and catastrophe in one neat orbital package. Its name is practical rather than poetic. Many stars carry catalogue numbers instead of grand titles. 55 Cancri refers to the host star system. The little letter E marks the order in which planets were identified around it. That means the planet was not named for elegance. It was named the way folders are named in an office. Yet behind this administrative label is something extraordinary. 55 Cancri E is what astronomers call a super-Earth. That term does not mean super in the heroic sense. It simply means a rocky planet larger and more massive than Earth, but much smaller than gas giants like Jupiter or Saturn. Think of it as a category between familiar terrestrial worlds and enormous gaseous ones. We do not have a super-Earth in our own solar system, which already makes such planets intriguing. They are common in the galaxy, yet absent from our local lineup, rather like discovering that every neighbouring town has bakeries we somehow forgot to build. This planet is roughly twice Earth's diameter and several times Earth's mass. That means stronger gravity, denser materials, and internal pressures that can become extreme. Already you can begin to see why people started imagining diamonds. Carbon under immense pressure can crystallize into diamond. If a world were rich in carbon and squeezed hard enough over long periods, then perhaps enormous diamond layers might form deep below the surface. It is a thrilling idea. Newspapers loved it. Headlines practically wrote themselves. A diamond planet, a cosmic gemstone, treasure beyond measure. One could almost hear calculators waking up around the world. Yet astronomy is usually more complicated than headlines. Scientists proposed the diamond possibility based on early data about the star and planet composition. Later studies suggested the situation may be less certain. The star may not be as carbon-rich as once thought. The planet may contain silicates, iron, magma, volatile layers, or combinations still debated. In other words, 55 Cancri may not be a giant cut jewel waiting in space. It may be something stranger and more interesting, a dynamic world whose true makeup resists simple labels. And then there is the heat. This planet orbits astonishingly close to its star. Very close. So close that a full year there lasts less than one Earth day. Imagine celebrating birthdays more often than breakfast. By the time you have found the candles, several birthdays have already passed. Because it is so near its star, temperatures on the day side may climb high enough to melt rock. Not merely warm stone, not pleasantly sunlit pebbles, but actual molten landscapes. Entire regions may exist as magma seas or lava plains, glowing under relentless radiation. If Earth's oceans are places of waves, tides, currents, and life, then the possible oceans of 55 Cancri would be oceans of fire-coloured liquid stone. Even that phrase deserves a moment. Liquid stone. We speak of rock as permanent, solid, dependable. Mountains stand for endurance, cliffs symbolise strength. Yet under enough heat, rock becomes fluid. It can flow, pool, splash, harden, melt again. On this distant world, what we treat as the most stubborn material may behave like weather. Many researchers suspect the planet is tidally locked, meaning one side continually faces the star while the other remains turned away. If so, one hemisphere may endure endless day and severe heating, while the opposite side knows perpetual darkness. Between them could lie gradients of temperature difficult to imagine, regions where molten material circulates and vaporized minerals drift through an exotic atmosphere. And yes, atmosphere. Perhaps not the kind one would request for a weekend retreat. Some observations suggest gases may rise from the hot surface itself. On worlds this extreme, rock can vaporize. Sodium, silicon monoxide, carbon compounds, mineral vapors, all may play roles depending on conditions. The sky, if there is one in any familiar sense, may be fed not by forests or oceans, but by the evaporation of the ground beneath it. There is something wonderfully humbling about that. On Earth, soil supports life. On 55 Cancri, the ground may attempt to become air. Astronomers have also noticed puzzling changes in emitted heat from the planet over time. Some measurements suggested its hot side became hotter or cooler between observations, leading to theories about volcanic activity, shifting atmosphere, circulating lava, or clouds of mineral vapor changing how heat escapes. Imagine scientists across light years of distance trying to infer volcanoes from tiny flickers of infrared light. It is detective work on a cosmic scale, and this is worth appreciating quietly. We have never walked there. We have never scooped a sample into a jar. No spacecraft has descended through those possible vapors with a cheerful beep. We know this world through starlight mathematics, repeated observations, patient doubt, and careful imagination disciplined by evidence. Humanity, from one small planet, notices another world far away and begins asking what its rocks are doing at night. That is a lovely species trait to have. Now, if the phrase diamond planet makes you picture glittering beaches and sparkling hills, let us gently adjust the brochure. Any diamonds that do exist would likely be deep under crushing pressures, mixed with other materials altered by heat, perhaps nowhere near the romantic surface fantasy. You would not stroll across shining gem fields in comfortable shoes. More likely, you would encounter temperatures that erase footwear as a concept. Still, the nickname survives because it captures something real beneath the exaggeration. 55 Cancri is a world where pressure, chemistry and geology may create forms of matter uncommon on Earth's surface. It reminds us that planets are laboratories. Given enough mass, enough heat, enough time, matter reorganizes itself into astonishing possibilities. There is another reason this world fascinates scientists. It belongs to a planetary system unlike our own. Multiple planets orbit the same star, each with different distances and likely different stories. Studying such systems helps us understand how planets form and migrate. Did 55 Cancri form where it is now, scorched beside its star, or did it begin farther out and move inward over ages? Did giant neighbours influence its path? Was it once cooler, then dragged into a harsher orbit? Every answer teaches us something not only about that system, but about the restless architecture of planetary systems everywhere. Our own solar system can make us think planetary order is normal, small rocky worlds inside. Gas giants outside, ice farther still, neat enough to print in textbooks. But the galaxy seems fond of chaos, rearrangement, crowded orbits, giant planets hugging stars, eccentric paths, and rocky worlds where oceans are made of magma. We may be orderly locals in a rather inventive neighbourhood, and perhaps that is why this story suits a sleepy hour. It is calming in its own strange way to remember that reality is larger than routine. While dishes wait in sinks, emails linger unanswered, and tomorrow's errands gather politely in the background. There also exists a planet where a year ends before your coffee cools, where stone may move like water, and where scientists debate whether carbon below the surface has become crystal. Your concerns may still matter, but they share space with marvellous absurdities. If we could watch sunrise there, assuming one hemisphere experiences anything like a shifting horizon, the light would not resemble ours. The parent star would loom larger in the sky. The landscape might glow from below as much as above. Heat shimmer could distort distance. Pools of molten material might reflect red and white light in trembling patterns. The ground could crack, reform, and release gases. It would be beautiful in the same way furnaces are beautiful from a safe distance. Fortunately, we're keeping a very safe distance. Back here on Earth, we can appreciate a more modest arrangement. Oceans of water. Skies one can breathe. Rocks considerate enough to remain mostly solid beneath our feet. A day length long enough to finish a sandwich before New Year celebrations begin again. Familiar comforts become more noticeable after meeting worlds that lack them. If we are going to understand a world like 55 Cancri, it helps to begin not with lava or diamonds or headlines, but with location. Strange planets become a little less mysterious when we know where they live. So tonight, let us drift outward gently and ask a simple question. Where in the universe is this place? The short answer is that 55 Cancri is relatively close by cosmic standards. It orbits a star system about 41 light-years from Earth. Now, 41 light-years may not sound especially close if you are thinking in human travel terms. If your car is unreliable, even 41 kilometers can feel emotionally significant. But in astronomy, where the Milky Way galaxy spans roughly 100,000 light-years across, 41 is almost nearby enough to borrow sugar from. A light-year, as you may know, is the distance light travels in 1 year. Light moves at about 300,000 kilometers per second, which is fast enough to circle Earth more than 7 times in a single second. So when we say this planet is 41 light-years away, we mean the light reaching our telescopes tonight left that system 41 years ago. While it was travelling toward us, fashions changed, technologies improved, children became adults, and someone somewhere probably still forgot their password. That also means we never see distant worlds exactly as they are now. We see them as they were when their light began the journey. Astronomy is a form of time travel in reverse. We do not leap into the past ourselves. The past arrives quietly through photons. The star that 55 Cancri E orbits is known as 55 Cancri, a name that sounds like either a catalogue entry or a hotel room with excellent views. It lies in the constellation of Cancer, traditionally represented as the crab. If you're wondering how a crab became associated with a planetary system containing blazing superheated worlds, you are not alone. Ancient sky naming was imaginative, practical, and occasionally unconcerned with future branding consistency. Constellations, of course, are patterns we humans draw across the sky. The stars within them are usually not physically connected in neat little symbolic shapes. They only appear arranged from our viewpoint. Cancer is one of the zodiac constellations, though considerably less flashy than some of its neighbours. It does not dominate the night sky with obvious bright stars. It is subtler, quieter, a constellation that asks for patience rather than applause. There is something fitting about that. Hidden in a modest patch of sky is a system that has become famous for one of the strangest planets we know. If you are standing somewhere dark enough to see Cancer clearly, away from city lights, and perhaps wrapped in a blanket with no immediate responsibilities, you could look toward that region and know that around one of those stars circles a world of intense heat, compressed matter, and possible molten landscapes. The night sky becomes more intimate when you know specific stories attached to tiny points of light. The host star, 55 Cancri, is often described as a sun-like star, though with important differences. It is a G-type star, similar in broad category to our own Sun, but somewhat smaller, cooler, and older. Think of it less as a twin, and more as a relative who resembles the family line but has made distinct life choices. Its age is estimated to be several billion years, possibly older than our Sun. That means this system has had a long time for planets to form, migrate, collide, settle, or remain gloriously unstable depending on circumstance. By the time life on Earth was figuring out multicellular experiments, 55 Cancri had already been shining for ages. Stars are not merely lights in space. They are anchors of systems, engines of chemistry, and weather makers on planetary scales. Every planet around them is shaped by distance, radiation, gravitational interactions, and historical accidents. Move Earth inward a little, and our oceans suffer. Move Jupiter closer, and the architecture of the solar system changes dramatically. Put a rocky world extremely close to a mature star, and you may get something like 55 Cancri E. This system is especially interesting because it is not a one-planet arrangement. Several planets have been detected orbiting 55 Cancri. That makes it a family, not a solitary story. There are worlds farther out, worlds more massive, worlds with different orbital periods and likely different compositions. Some may be gas giants, others may be intermediate types. Each one tells part of the system's history, and here is something worth pausing over. For most of human history, we did not know whether other stars had planets at all. It was suspected, hoped for, debated, imagined. Then gradually, with better instruments and stubborn patience, we began finding them. Now we know planets are common. Many stars host them. Some host several. Nature appears to enjoy making worlds. That shift in perspective is profound. The night sky used to feel like stars alone. Now it feels populated. Among those planets in the 55 Cancri system, 55 Cancri E is the innermost famous overachiever. It races around its star at astonishing closeness. Its orbital distance is tiny compared with Earth's comfortable spacing from the Sun. If Earth is seated at a sensible distance from the campfire, 55 Cancri E has practically climbed into the flames. Because of this proximity, its year lasts less than one Earth day, around 18 hours. Imagine living somewhere that celebrates New Year several times before you have answered 2 emails. Calendars there would require emotional resilience. This closeness also means the star appears much larger in the sky than our Sun appears from Earth. Not because the star itself is enormously larger, but because the planet is so near to it. If you could somehow stand on the hot side of the planet, Ignoring all survival concerns for a moment, the star would dominate the heavens. It would be less like our sun hanging in spacious blue daylight, and more like a constant blazing presence overhead. The geometry of planetary systems matters deeply. Distance controls, temperature, orbital speed, tidal forces, and radiation exposure. A small change, inward or outward, can transform a world completely. Earth's oceans exist partly because we orbit in a range where liquid water can persist. Mercury, much closer to the Sun, endures fierce temperature swings. Venus, only a bit closer than Earth, became a crushing greenhouse inferno. That lesson alone should make us humble about assuming planetary outcomes. 55 Cancri takes that lesson and turns it up considerably. Now, when astronomers say this system is 41 light-years away, another comforting truth hides inside the number. The planet is distant, yes, but not unreachable forever in the imaginative sense. We cannot travel there with present technology in any practical human timescale. Yet it is close enough for repeated study. Telescopes can observe transits, measure stellar wobble, examine thermal emissions, refine orbital data, and continue learning. It belongs to the category of worlds we can meaningfully investigate rather than merely speculate about. That matters. Some exoplanets are so far away they remain statistical curiosities. We know they exist, but details are sparse. 55 Cancri is closer, brighter in scientific terms, and more cooperative with observation. It has become a laboratory for studying hot, rocky planets beyond our solar system. Let us talk for a moment about how we locate such places mentally, because numbers alone can feel dry. 41 light-years means that if you sent a radio message today, and if anyone there had a receiver and excellent manners, the fastest possible reply would not return for 82 years. It means the nearest generation of children could send greetings, and their grandchildren might hear the answer. It means distance in space often doubles as distance in patience. Yet compared with the scale of the galaxy, it is local. There are stars thousands of light-years away whose planets we also study. There are galaxies millions of light-years distant whose light began travelling before humans existed in modern form. Seen against that backdrop, 55 Cancri is practically in the neighbourhood. If our Milky Way were reduced to the size of a continent, this system would still be in our regional map. Not next door certainly, but close enough to point at during a family argument. There is another layer to location: motion. Nothing in the cosmos is standing still. Earth orbits the Sun. The Sun orbits the centre of the Milky Way. The Milky Way moves relative to neighbouring galaxies. The 55 Cancri system moves as well. So when we say where it is, we really mean where it is approximately, while everything involved continues gliding through space like an elaborate dance no one rehearsed. This can sound unsettling at first, but it is also reassuring. Movement is normal. Stability in the universe is often temporary balance, not perfect stillness. Even your quiet room right now is riding a planet that spins and circles a star at tremendous speed. You're already on a spaceship, it just has oceans. As astronomers refined measurements of the 55 Cancri system, they learned more about the star's brightness, mass, metallicity, and planetary companions. These details help estimate planet sizes, densities, and compositions. A planet cannot be fully understood in isolation because everything depends on the star. If the star flickers, ages, emits radiation differently, or has different elemental abundance, the planets inherit consequences. Our Sun shaped Earth's chemistry and climate profoundly. Likewise, 55 Cancri shapes 55 Cancri every moment through gravity and energy. The star is not background scenery. It is the reason the planet is what it is. Some listeners may wonder whether 41 light-years means anyone there could see us. In principle, if observers had powerful enough instruments and fortunate geometry, they might detect Earth transiting our Sun, or infer our presence through atmospheric signatures. More realistically, both civilizations would spend years arguing over budgets for telescope upgrades. Still, the thought is pleasant. While we study their lava world, someone there, entirely hypothetical and probably heat-resistant, might study our cloud-covered blue one. Cancer, the constellation where this system appears, is best seen in certain seasons depending on hemisphere and latitude. It contains a lovely star cluster known as the Beehive Cluster, visible to the eye under dark skies as a misty patch. Ancient observers noticed it long before telescopes. I like that image. In the same region of sky where humans once admired a soft fuzzy glow, we now identify planets with extreme geology and impossible temperatures. The sky does not change. Our understanding of it does. When you next look upward, it can be comforting to remember that many stars are not solitary sparks. They are homes to systems, histories, and worlds unlike anything we expected. Some may have ice mountains taller than Everest. Some may have winds faster than sound. Some may have oceans deeper than Earth's crust. And one of them, in this case, may have seas of molten rock and perhaps layers of carbon compressed into crystal far below. Location gives scale to wonder. It also gives perspective to ordinary evenings. Here we are, on a temperate world with breathable air, mild gravity, liquid water, and chairs that do not burst into flame. We sometimes overlook how luxurious this setup is. Learning where 55 Cancri resides can make Earth feel less ordinary and more fortunate. Now that we know where 55 Cancri lives, we can move closer to the conditions that define it. Some planets are shaped mainly by composition. Others by collisions long ago. Some by thick atmospheres, deep oceans, or magnetic fields. This world, however, is shaped first and foremost by proximity. It lives so near its star that distance itself becomes destiny. 55 Cancri E is not simply warm. It is not pleasantly tropical, not desert-like, not summer at noon with regrettable footwear choices. It is a planet exposed to such intense stellar energy that rock may melt across vast regions. Heat is not an occasional feature there, it is the governing principle. To understand why, imagine placing Earth closer and closer to the Sun. At first, climates would shift, ice would retreat, oceans would warm, weather patterns would become unstable. Move inward further and water would begin escaping. Greenhouse effects would intensify and habitability would collapse. Keep going, and eventually familiar geology would yield to something harsher, where the surface itself begins to soften under relentless radiation. 55 Cancri already lives in that final category. Its orbit is astonishingly tight. The planet circles its star in less than one Earth day, roughly every 18 hours. That means it races through a complete year, while most of us are still deciding whether to fold laundry today or postpone it with conviction until tomorrow. An orbit this close does more than heat a planet. It changes the mechanics of its existence. Gravitational forces become powerful, persistent, and deeply personal. The star pulls more strongly on the side nearest to it than on the side farther away. Over time, that uneven pull can reshape rotation itself through a process called tidal locking. Tidal locking sounds technical, but the concept is familiar. Our own moon is tidally locked to Earth. It rotates once in the same time it takes to orbit us, which is why we always see the same lunar face. The moon turns, yes, but in perfect rhythm with its orbit. Many scientists believe 55 Cancri is likely tidally locked to its star as well. If so, one hemisphere always faces the star, bathing in endless daylight, while the opposite side remains in permanent darkness. No sunrise, no sunset, no rotating parade of morning and evening. Just constant exposure on one side, constant night on the other. That alone makes daily life there difficult to schedule. On Earth, day and night create cycles that shape weather, biology, sleep, temperature gradients, and even culture. We wake with light, rest with darkness, and organize much of life around the turning planet beneath us. Remove that cycle, and the entire rhythm changes. On 55 Cancri, if tidal locking is complete, one side may never know darkness. Imagine a landscape where the star hangs eternally overhead, or near overhead depending on location, never dipping below the horizon. Shadows would not migrate across afternoons. They would remain, perhaps shortened or stretched by terrain, but not governed by a setting sun. Meanwhile, the far side would remain starless except for distant cosmic lights. No dawn ever arrives there, no golden edge of morning, only the cold side of a world whose other face burns. Yet even cold is relative. On a planet this extreme, the night side may still be far hotter than many places in our solar system, simply because internal heat transport, atmospheric circulation, and molten flows redistribute energy. Darkness there does not necessarily mean icy calm. It may mean less catastrophic warmth. Between these two hemispheres could exist a transitional region, sometimes called the terminator zone, where day meets night. On Earth, the terminator is always moving as the planet rotates. On a tidally locked world, it could remain nearly fixed, forming a permanent band around the globe. That band fascinates planetary scientists because in some tidally locked worlds, if conditions are moderate enough, such zones might be the most stable places. On 55 Cancri, however, moderation is in short supply. Even transitional regions may remain blisteringly hot, geologically active or chemically hostile. Still, it is interesting to imagine a ring around the planet where the star forever hovers on the horizon, where one direction leads toward brighter inferno and the other into endless dark. It sounds less like geography and more like mythology. The phrase eternal fire is not merely dramatic language. Temperatures estimated on the day side of 55 Cancri may rise to around 2000 degrees Celsius or more depending on models and observations. At such temperatures, many rocks melt. Metals soften or liquefy depending on composition. Surface materials can vaporize. Chemical bonds reorganize under conditions no human body was invited to witness. If you placed common earthly objects there, outcomes would be brisk. Wood burns, plastics fail, water cannot remain liquid, steel would suffer, electronics would protest briefly, then become decorative minerals. Even mountains behave differently under such heat. We tend to think of mountains as durable monuments, but under enough thermal stress, materials expand, fracture, slump, melt, and recycle. Landscapes on 55 Cancri may be dynamic in ways that make Earth's geological patience seem leisurely. Volcanoes there, if active, would not be quaint cones with tourist paths and warning signs. They could be vents in a globally heated crust, fissures releasing magma, mineral vapours, and gases into a sky already shaped by heat. Lava may not be local spectacle but widespread environmental reality. One of the most intriguing findings from observations has been evidence that the planet's thermal emission may vary over time. In simpler words, the amount and pattern of heat detected from the planet appear to change between measurements. That has led to several possibilities. Perhaps volcanic activity resurfaces regions with fresh molten material. Perhaps an atmosphere thickens or thins temporarily, changing how heat escapes. Perhaps clouds of vaporized minerals form and disperse. Perhaps currents in magma redistribute heat across the surface. Or perhaps multiple processes interact in ways not yet fully understood. Imagine astronomers studying a tiny distant point of light and realizing that even there, geology may be active enough to change what telescopes detect across years. A living surface, in a geological sense, revealed by faint warmth crossing space. Now let us consider gravity's role in eternal fire. Because 55 Cancri is more massive than Earth, it likely exerts stronger surface gravity. That means denser atmosphere retention may be possible depending on composition, and internal pressures become intense. It also means any molten material flows under different constraints than lava on Earth. Viscosity, pressure, mineral mix and heat transport could create behaviours unlike our volcanic systems. Then there is tidal heating. When a planet orbits very close to a star, gravitational flexing can generate internal heat, especially if the orbit has any eccentricity or if neighbouring planets perturb it slightly. Jupiter's Moonio experiences this around Jupiter and is the most volcanically active world in our solar system, largely because gravitational squeezing needs its interior. 55 Cancri may experience related effects, though in a very different environment. If so, the star is not only roasting the outside, it may also help stir the inside. That creates a grimly efficient arrangement. Heated from above, flexed from within, trapped in close orbit, rotating in synchrony. A world engineered by nature to test how much punishment rock can take before becoming fluid. And yet, for all its violence, there may also be a strange stability to it. Once tidally locked, once heated, once settled into its orbital pattern, the same side faces the star year after year after year. The inferno becomes routine. The darkness becomes routine. Even catastrophe can become climate when sustained long enough. There is something quietly profound in that idea. We often imagine extremes as temporary, storms pass, fires burn out, summers end, but on many worlds the extreme is simply normal. Earth teaches us moderation because we evolved here. Elsewhere, normal may include acid clouds, methane rain, crushing pressure, global ice shells, or skies bright enough to melt stone. The universe is generous with conditions and indifferent to our preferences. If one could safely observe the day side of 55 Cancri from orbit, the planet might appear incandescent in places, perhaps glowing with thermal radiation beyond visible human sight, perhaps showing hot patches where magma nears the surface. Depending on atmospheric behaviour, clouds might not be water, but mineral vapours or condensed rock species lofted and redistributed. Clouds made of rock sounds unreasonable, until one remembers that many truths of planetary science first sounded unreasonable. On the night side, the view could be equally astonishing. Imagine standing under permanent darkness while a horizon glows faintly from distant heat or volcanic regions. The star never rises, yet the planet may not be truly dark if molten features radiate from below. Instead of moonlight on water, perhaps dim red shine on stone. Of course, standing anywhere there remains a deeply flawed plan. What does tidal locking mean for weather? If any atmosphere exists in significant form, huge temperature contrasts between hot side and cool side can drive powerful winds as gases attempt to redistribute heat. Air rises over scorching regions, flows aloft, descends elsewhere, then returns. On some exoplanets, such circulation may reach extraordinary speeds. Whether 55 Cancri hosts enough atmosphere for this to happen robustly remains debated, but the principle is important. Day and night are not just lighting conditions, they are engines of motion. It is also worth noting that tidal locking does not always mean the star sits perfectly overhead at one point forever, in the simplistic sense. Orbital eccentricity, libration effects, resonance states, and atmospheric influences can complicate matters. But the broad picture remains. The same hemisphere strongly favours facing the star. Even timekeeping becomes peculiar on such a world. Earth's clocks derive psychologically from rotation: sunrise, noon, sunset, midnight. On 55 Cancri A, what marks a day if the sky does not change? You might track the orbit itself, but from the locked surface that orbit does not bring traditional daylight cycles. Clocks become abstractions rather than companions of nature. Perhaps that is fitting for a planet where ordinary categories already struggle. There is a temptation to call worlds like this hellish, but that word reflects human discomfort more than scientific clarity. 55 Cancri E is not evil. It is not cursed. It is simply obeying physics under conditions different from ours. Carbon, iron, silicates, gravity, radiation, orbital mechanics, thermodynamics, nothing supernatural required, and in that sense, it is elegant. Stars form from collapsing clouds. Disks of material swirl around them, planets accrete, migrate, collide, settle. Some end up temperate, some frozen, some gaseous, some tidally locked and burning beside their stars. Each outcome is a variation on the same universal toolkit. The more we learn this, the more precious Earth's balance appears. Oceans of water instead of magma, a rotating globe with regular nights, seasons that challenge us but do not melt continents, a star at useful distance rather than overwhelming nearness. Familiarity often hides luxury. Still, it would be a mistake to see 55 Cancri A only as a warning. It's also a gift to science. Such extreme worlds reveal how planets behave at the limits. They test models of atmosphere retention, rock vaporization, heat transport, tidal evolution, and internal composition. They help us understand not just themselves, but planetary diversity everywhere. And for a tired mind preparing for sleep, there can be comfort in knowing the universe is busy conducting grand experiments far away, while you need only rest. When we hear the word ocean, most of us picture something deeply familiar. We imagine water stretching toward a horizon, waves folding under wind, tides rising with patient rhythm, sunlight scattering across moving blue surfaces. Oceans on Earth smell of salt, carry storms, cradle life, and reflect skies that change by the hour. Even those who live far inland usually understand an ocean instinctively. It is one of the oldest images in the human mind. Now let us set that image aside, gently and completely. On 55 Cancri E, if current interpretations are close to correct, the nearest equivalent to an ocean may not be made of water at all. It may be made of molten rock, seas not of blue liquid, but of glowing silicate material, heated beyond solidity, flowing across a world too close to its star for stone to remain reliably stone. If Earth teaches us that oceans carve continents, this distant planet may teach us that continents themselves can become oceans. That is one of the strangest lessons in planetary science. The materials are often the same everywhere. Silicon, oxygen, iron, magnesium, carbon, nickel, calcium. Rearrange temperature, pressure, gravity and time, and familiar matter behaves in unfamiliar ways. Water freezes into glaciers, boils into vapor, or falls as rain depending on conditions. Rock can do the same sort of identity shift, though with far less hospitality. The reason scientists speak of possible lava oceans on 55 Cancri A is simple in principle, even if complex in detail. The planet's day side likely reaches temperatures high enough to melt large portions of its crust or mantle-derived surface material. If the same side continually faces the star, then stellar heating remains relentless. There is no cool night to reset the landscape, no evening breeze, no seasonal relief. Heat arrives, stays, and keeps negotiating with stone until stone gives in. Picture a shoreline there, if such a word still applies. Instead of foam, perhaps slow rippling magma. Instead of gulls, none at all. Instead of driftwood, fragments of cooling mineral crust carried and broken by currents of liquid rock. Instead of a pleasant walk, immediate regret. Lava on Earth usually appears in episodes. A volcano erupts, a fissure opens, basalt rivers forward, then cools. Even the largest flows are events, dramatic but temporary. On 55 Cancri E, molten rock may be environmental background rather than temporary crisis. Imagine if Hawaii's lava fields, Iceland's fissures, and Earth's deep mantle temperatures all move from occasional spectacle to daily geography. Of course, we should be careful. We have not photographed neat postcard scenes of lava surf rolling onto black beaches. Much of what we infer comes from temperature measurements, mass radius estimates, thermal phase curves, and models of how rock behaves under such irradiation. Science often works by assembling a picture from indirect clues. Still, those clues strongly suggest that surface melting on this world is not a minor detail. Let us think about what a lava ocean would actually be. Molten rock is not identical to water in behaviour. Its viscosity depends on composition and temperature. Some magmas are runny, flowing relatively easily, like basaltic lava on Earth. Others are thick, sticky and slow, resisting movement while trapping gases. The exact chemistry of 55 Cancri matters enormously. A magma sea rich in certain silicates may move differently than one enriched in other minerals. Iron content, volatile content, crystal fraction, temperature gradients, all shape motion. That means these oceans may not look like smooth earthly seas. They may resemble sluggish glowing plains in one region, turbulent churning basins in another, crusted surfaces rafting atop hotter material elsewhere. Some zones may develop thin, cooled skins that crack and sink repeatedly, like burnt sugar disturbed by a spoon. Other areas may remain open and radiant, and yes, radiant is the correct word. Molten surfaces emit energy strongly. Depending on temperature, some regions might glow dull red, orange or brighter if seen directly under suitable conditions. Much radiation would also lie beyond visible light, in infrared wavelengths that telescopes detect more readily than human eyes would appreciate. There is something almost humorous about that. We imagine alien beauty in crystal forests or turquoise skies, and instead nature offers us a planet that may resemble an industrial furnace the size of a world. Yet furnaces can be beautiful. Now consider waves. Would a lava ocean have them? Possibly, though not like water waves on Earth. Any fluid surface can support waves if forces disturb it. Wind, gravitational tides, seismic activity, impacts, convection from below, or circulation patterns could generate movement. The speed and shape would depend on density, viscosity, depth, and surface tension. Instead of playful surf, one might see slow swells of incandescent material or heavy rolling ridges moving with deliberate menace. Tides are another possibility. Since the planet orbits close to its star, gravitational interactions are intense. If orbital eccentricity or companion planets induce even modest variations, tides in molten regions could occur. Imagine a star raising tides not in water, but in magma, a planetary surface literally flexing and lifting under celestial pull. That phrase deserves a quiet pause. We often speak of tides as moonlit coastal phenomena, but tides are simply gravity-shaping fluids and deformable bodies. On 55 Cancri E, the fluid may be rock. Then there are currents. Earth's oceans move heat around the globe through vast conveyor belts driven by wind, salinity, temperature differences, and planetary rotation. A magma ocean would have its own circulation logic. Hotter material rises, cooler material sinks. Dayside heating may drive flows outward from intensely irradiated zones. Slightly cooler material may crust, thicken, fracture and recycle downward. Internal heat from the mantle could add upward plumes. The result may be an ocean that never truly rests because the entire system remains out of thermal balance. Heat pours in from above, possibly rises from below, and seeks escape through movement, radiation, and geological turnover. Hence, oceans that never rest. On Earth, the sea can appear calm while deep currents move invisibly below. On 55 Cancri E, even apparent stillness may conceal convection cells kilometers deep, molten circulation transporting minerals, temperature, and chemical species across the planet's surface and shallow interior. What happens when lava cools at the margins? Crust forms. That crust may float temporarily atop denser melt, fracture under stress, collide with neighbouring plates of cooled material, sink where heavier, remelt where reheated. One can imagine a patchwork of temporary rafts drifting over incandescent depths, tectonics in miniature, constantly erased and rewritten. There may be shorelines that do not stay put, basins that fill and drain over geological time, regions where repeated resurfacing smooths craters and hides ancient scars. In such a place, maps would age poorly. Even the atmosphere, if present, may be tied directly to these oceans. On a sufficiently hot world, molten rock can release vaporized components. Sodium, potassium, silicon monoxide, oxygen-bearing compounds and other species may enter the air. As gases move to cooler regions, some may condense and fall back as mineral rain or deposit as solids. Rain made from rock vapor sounds excessive, but planetary science has little interest in moderation. Think of the water cycle on Earth. Oceans evaporate, clouds form, rain falls, rivers return water to sea. On 55 Cancri E, an analogous cycle could involve evaporating minerals, atmospheric transport, condensation, and return to molten basins. A weather system built from geology rather than hydrology. If you listened from orbit, there would be no crashing surf in any earthly sense because sound requires atmosphere, and conditions may be thin or strange. But if enough air existed, and if one could survive long enough to appreciate acoustics, perhaps there would be groaning crust, bursting gas pockets, cracking plates, distant roars of overturning magma, and the low thunder of a planet continually remaking itself. One of the fascinating puzzles about 55 Cancri A is that observations have suggested changes in emitted heat over time. Some data implied the hottest region may shift or the overall brightness may vary. That can happen if the surface changes. Fresh lava exposed by volcanism emits differently than older crust. Clouds or atmospheric veils can mask hotter layers. Circulating magma can redistribute heat. In short, astronomers may be watching not a static glowing bead, but an active world with moods. That is remarkable when you remember the distance involved. We detect slight changes in light from 41 light-years away and infer lava behaviour. Humanity can be wonderfully nosy. Let us compare this to Earth for perspective. Our oceans regulate climate, store carbon, feed ecosystems, and shape civilizations. They are gentle enough to sail, dangerous enough to respect, and chemically ideal for life as we know it. Water's unusual properties make biology possible in countless ways. A lava ocean does none of that for creatures like us. It sterilizes, radiates, recycles crust, and reminds organic chemistry to remain elsewhere. Yet from a planetary standpoint, it also regulates heat, transports material, and influences atmosphere. It is an ocean performing planetary functions through entirely different chemistry. This is a recurring theme in exoplanets: familiar roles, unfamiliar actors. Could the entire dayside be molten? Perhaps not uniformly. Some models suggest localized magma seas, others broader global melt zones depending on albedo, atmosphere, circulation and composition. Some regions may remain solid but softened, others may alternate between crust and melt. Science here deals in probabilities, not tourist brochures. Still, whether partial or extensive, the existence of persistent molten surface regions would place 55 Cancri A among the most extreme rocky planets known. Now imagine standing, impossibly protected, on a cliff above such a sea. The horizon shimmers beneath a huge glaring star fixed in the sky. The ground beneath you is dark rock veined with heat. Far below, a basin of orange-black liquid rolls slowly, crust plates forming and breaking like charcoal skin on soup no one should taste. Gas plumes rise and drift. Occasional bursts reveal brighter depths. Nothing green grows, nothing cools, no gull crosses overhead because even gulls know boundaries. And yet, it would be unforgettable. There is also a deeper scientific importance to worlds like this. They may resemble stages Earth itself once passed through. Early in its history, after giant impacts and during intense accretion, our own planet likely hosted magma oceans. Before blue seas came molten seas. Before continents, glowing crust. Before weathering rain, rock vapor and impact fire. So when we study 55 Cancri E, we may also glimpse something ancient about terrestrial planets in general. Not our future, perhaps, but our distant beginnings. That connection is comforting in an unexpected way. Even impossible worlds are part of the same family tree. Earth and 55 Cancri formed from cosmic dust around stars. Both are outcomes of gravity sorting matter. One cooled into forests and tides. The other remained or became a furnace world. Different endings from similar ingredients. And perhaps that should make us grateful for our version. The cup beside you likely contains liquid at a temperature compatible with fingers. The floor under you is stable. Your nearest ocean, if distant, consists of water rather than basaltic melt. These are luxuries easy to miss until compared with alternatives. When we speak of a sky, most of us imagine something gentle and familiar. Blue daylight spread above rooftops, clouds drifting in layers, evening colours fading into stars, air moving softly through trees. A sky, in ordinary life, feels less like an object and more like a background comfort. We rarely think about it until weather changes or sunsets insist on attention. Earth's sky is so dependable that we forget how unusual it is. It is transparent enough for sunlight, thick enough to protect life, rich enough in oxygen for lungs, balanced enough to support water cycles, winds, seasons, and temperature stability. It softens radiation, scatters blue light, carries birds, storms, pollen, and the smell of rain. Our atmosphere is not just scenery, it is infrastructure. Now let us leave that behind and look upward on 55 Cancri. If the surface of this world can melt, if rocks can vaporize, if heat dominates both day and geology, then the sky above such a planet may not be the kind one breathes. It may be the kind one studies from a very respectful distance. A sky made not from oceans and forests and biological cycles, but from the planet itself being slowly cooked into gas. That is one of the most astonishing ideas in exoplanet science. On some worlds, the atmosphere may be born less from ancient seas and more from evaporating stone. Because 55 Cancri orbits so close to its star, the day side likely experiences extreme temperatures. Under such heat, minerals that remain solid on Earth can release atoms and molecules into the surrounding space. Elements like sodium or potassium, compounds involving silicon and oxygen, carbon-bearing gases and other species may escape hot surfaces or volcanic sources. In simpler terms, the ground may help make the sky. Imagine walking across a desert so hot that sand becomes vapor and joins the air. Then imagine that scaled to a planet. That is the sort of environment we are discussing. We should be careful here, as always. Scientists are still debating exactly how thick the atmosphere of 55 Cancri is, what it contains, whether it changes over time, and how much of the observational signal comes from gas versus molten surface versus instrumental challenges. Exoplanet science is often a patient conversation between evidence and uncertainty. Still, uncertainty does not make the subject less interesting. It often makes it more honest. Let us begin with the simplest possibility, a thin atmosphere constantly replenished by the hot surface. On Earth, if our atmosphere vanished tomorrow, that would be a catastrophe. On 55 Cancri, a thin atmosphere might struggle to survive because intense stellar radiation can strip gases away over time. Ultraviolet light, charged particles, and heat-driven escape can erode an atmosphere, especially on worlds close to active stars. That means if gases are present, they may need continual replacement through volcanic outgassing, mineral evaporation, or internal sources, so the sky there may be less like a permanent blanket and more like a system under constant repair. That alone changes how we think of weather. Earth's atmosphere is ancient, dynamic, and largely persistent. 55 Cancri may host a sky that must keep remaking itself just to remain there. Now imagine the appearance of such a sky. Would it be blue? Probably not in the earthly sense. Blue skies on Earth come from Rayleigh scattering, where small molecules like nitrogen and oxygen scatter shorter wavelengths of sunlight efficiently. Different compositions, Different particle sizes, haze layers, and different stellar light conditions can produce entirely different colours. A mineral-rich atmosphere might glow in reds, oranges, browns, greys, or pale metallic tones, depending on composition, density, and illumination. Suspended particles from vaporized rock or volcanic plumes could create haze. Condensed mineral droplets might reflect light strangely. Heat itself could make lower layers luminous. In some regions, the sky may not simply reflect the star, it may radiate its own light. That phrase sounds dramatic, but hot gases emit thermal radiation. A sufficiently heated atmosphere can glow, especially near the surface where temperatures are highest. Instead of cool blue openness overhead, one might see a dim furnace-bright dome, brighter near the horizon where depth through the atmosphere is greater. If you have ever looked into the opening of a kiln, a foundry or industrial furnace from a safe distance, you know that heated air can appear alive with shimmer and brightness. Scale that upward into planetary dimensions, and you begin to approach the mood of such a world. Of course, breathing would not be on the itinerary. Even if oxygen existed in trace forms chemically, the temperatures alone would make lungs irrelevant. But composition matters too. A sky containing sodium vapour, carbon monoxide, carbon dioxide, sulfur species, silicate vapours, or oxygen released from broken minerals would be hostile in numerous overlapping ways. The universe is efficient at creating multiple reasons not to inhale. There is also the matter of pressure. We do not yet know precisely how dense any atmosphere there may be. It could be thin and tenuous, thick and dynamic, or variable over time. Some studies have suggested that observed temperature differences may require a substantial atmosphere capable of redistributing heat. Others argue molten surface transport may explain more than air does. The debate continues. That debate itself is exciting because it means the world is complex enough to resist easy answers. Suppose there is a thicker atmosphere, then winds could become extraordinary. On a tidally locked planet, one side receives continuous stellar heating while the far side remains much cooler. Such stark contrast drives circulation. Hot gases rise on the day side, move aloft toward cooler regions, descend elsewhere, and return. The larger the temperature difference, the stronger the engine. On some hot exoplanets, models predict winds travelling at thousands of kilometers per hour. If 55 Cancri sustains significant atmosphere, air may race from blazing hemisphere to dark hemisphere in constant planetary scale currents, not breezes through leaves, rivers of gas trying to solve an impossible heat problem, and if suspended ash, droplets, or mineral condensates ride those winds, then weather becomes geology in motion. Imagine clouds not of water, but of condensed rock vapour, tiny particles forming high above the hot side, then drifting into cooler zones where they thicken or fall. Rain not of water, but droplets or grains of minerals. Snow, perhaps, in some local sense, though no child would wish to catch it on their tongue. We already know of worlds where iron may condense in clouds and rain on the night side. So while rock clouds sound theatrical, nature has precedent for stranger things than our instincts allow. There is another possibility, an atmosphere that comes and goes. Because the planet may experience volcanic resurfacing, lava flows, shifting crust, and variable thermal conditions, the gases released could change over time. A burst of volcanism might thicken local haze. Fresh molten surfaces may outgas more intensely. Cooling crust could reduce emissions. Atmospheric escape to space may constantly remove lighter components. The result could be a sky in flux over years, decades, or geological spans. Not stable weather, but episodic breathing of the planet itself. That is an interesting inversion of language. We breathe air. This planet may breathe rock. Now let us imagine standing there again, impossibly protected by fictional technology and excellent insurance. Above you, no soft blue dome. Instead, a star fixed in the sky, immense and punishing. Around it, an atmosphere hazed with glowing particles. The horizon bright with suspended dust and heat shimmer. plumes rising from distant vents, winds carrying mineral mist. Perhaps faint sparks where hot grains collide, the air itself heavy with radiance. You would not look up for peace, you would look up in astonishment. Nightside conditions could be equally compelling. If the atmosphere circulates globally, gases transported to darkness may cool and condense. The sky there might clear in places, revealing stars above a black landscape warmed only by internal heat and redistributed energy. In other regions, strange clouds could drift overhead, illuminated faintly by glowing lava fields or scattered light from the distant dayside horizon. A permanent night under alien clouds is no less dramatic than eternal day. Earth's atmosphere gives a sense. Salt air, pine air, rain-soaked streets, summer grass. Those sensory details are tied to chemistry and biology. On 55 Cancri, any scent would be impossible for us to tolerate and perhaps impossible to survive long enough to describe. But conceptually, imagine the smell of hot metal, volcanic vents, scorched minerals and electrical storms mixed together. Then imagine deciding not to visit. There is also the question of sound. If the atmosphere is thick enough, winds would howl across terrain, vents would roar, falling mineral particles might hiss against hot surfaces, and thermal cracking crust could echo. If it is thin, sounds would be muted, strange, delayed. Either way, the soundtrack would be less seaside retreat and more planetary machinery. Why does this matter scientifically? Because atmospheres are storytellers. They reveal internal composition, volcanic activity, temperature structure, magnetic shielding, escape processes, and planetary history. When astronomers analyse light passing through or emitted from a planet's atmosphere, they are reading clues. Tiny changes in starlight can indicate sodium, hydrogen, water vapour, methane, carbon dioxide, or stranger species depending on the world. For 55 Cancri E, every observation helps answer deeper questions. Is this truly a bare lava world with only wisps of gas? Is there a substantial envelope of volatile material? Does the atmosphere evolve rapidly? Is the planet losing gases to space? Are we seeing signatures of geology in real time? These are not small questions. They help us understand how rocky planets survive or fail under intense irradiation. There is something humbling in that. Our own atmosphere feels permanent because it surrounds us every second of life. Yet atmospheres can be lost, transformed, stripped away, poisoned, rebuilt, or never formed in the first place. Worlds are fragile in different ways. Earth's breathable sky is not guaranteed by the universe. It is a particular success story. Learning about skies that glow instead of breathe can make our ordinary air feel more precious. The next easy inhale through an open window becomes less mundane when you remember that some planets wear vapours of stone. And perhaps that is one quiet gift of astronomy. It returns gratitude to familiar things. You need not travel 41 light years to appreciate a good atmosphere. You can notice it in the coolness of evening, the softness of wind, the fact that clouds carry rain instead of silicates, and that the horizon does not emit furnace light. Long before most people had heard the name 55 Cancri E, the planet became famous for a nickname. Not because it was the hottest known world, or the fastest orbiting rocky one, or even because lava may cross its surface. It became famous because someone said, in essence, that it might be made of diamond. That is the sort of phrase the modern world cannot resist. A diamond planet. Instantly, imaginations wake up. Headlines sparkle. People who had not thought about exoplanets since breakfast suddenly become interested in orbital mechanics. It sounds glamorous, excessive, and slightly suspicious, which in fairness describes many successful headlines. Yet the nickname did not come from nowhere. It emerged from genuine scientific reasoning, early measurements, and a fascinating question about how planets form when chemistry differs from what we know at home. To understand why scientists began using that phrase, we need to talk not about jewellery, but about carbon, pressure, stars, and the tendency of matter to surprise us. On Earth, most rocks are dominated by oxygen combined with silicon, magnesium, iron, calcium, and aluminum. Our planet formed in a region and from materials where those elements became common building blocks. Granite, basalt, mantle minerals, crustal silicates all reflect that chemistry. Carbon exists too, of course, but in relatively small proportions compared with the bulk rocky framework. Carbon on Earth is better known for joining life than building continents, but planetary systems can differ. Stars form from giant clouds of gas and dust, and the exact mix of elements in those clouds varies from place to place. If a star and its surrounding disk contain different ratios of carbon to oxygen, then the solids condensing during planet formation may differ as well. Instead of silicate-dominated worlds like Earth, perhaps some systems could build planets rich in carbon compounds. That possibility is where the story begins. Early studies of the 55 Cancri star suggested it might have a relatively high carbon-to-oxygen ratio. If true, then planets forming in that system could have incorporated more carbon-rich material than Earth did. Combine that with measurements showing 55 Cancri A was dense and rocky, and some researchers proposed a bold interpretation. Perhaps this world contained large amounts of carbon in forms such as graphite, carbides, and, under immense pressure, diamond. That was scientifically interesting even before the nickname arrived. Then the nickname arrived, and it arrived wearing expensive shoes. The media quickly translated a nuanced compositional hypothesis into something far simpler and shinier. Diamond planets spread everywhere. Many readers pictured a glittering sphere the size of Earth floating through space like a luxury item misplaced by the cosmos. Some imagined mountain ranges of gemstones. Others quietly considered mining rights despite lacking spacecraft, permits, or realism. This is a recurring event in science communication. A careful paper says, under certain assumptions, internal layers may include substantial crystalline carbon phases. A headline says, Space treasure ball found. Still, behind the simplification lies a real and useful concept. Let us unpack it gently. Diamond is simply carbon arranged in a specific crystal structure under the right conditions of pressure and temperature. On Earth, natural diamonds form deep in the mantle where carbon experiences immense pressure over long periods. Volcanic processes then transport some diamonds upward through kimberlite eruptions. That means diamonds are not magical. They are geological outcomes. If a planet several times Earth's mass formed with abundant carbon and experienced enormous internal pressures, then diamond layers inside such a planet become plausible. Not certain, not guaranteed, but plausible. And 55 Cancri certainly offers pressure. Because the planet is more massive than Earth, gravity compresses its interior strongly. As depth increases, materials are squeezed to extremes far beyond ordinary surface experience. In planetary interiors, pressure is not a minor detail. It changes mineral structures, melting points, conductivity, and density. Carbon under those conditions may adopt forms very different from soot in a fireplace or pencil graphite on paper. So the original idea was never that the surface is a giant engagement ring. It was that the interior might contain carbon-rich layers, perhaps including diamond. That distinction matters greatly. If you dug into Earth deeply enough, you would encounter exotic high-pressure minerals unfamiliar at the surface. Likewise, if 55 Cancri A contains diamond, it may be buried beneath crust, magma, mantle layers, or transformed zones inaccessible to any imaginary tourist carrying a shovel and poor judgment. Another important point is that diamonds on Earth are stable under certain conditions. But 55 Cancri is not Earth. Surface temperatures on the star-facing side may be high enough to melt rock. Carbon exposed near the surface might exist as graphite, vapor compounds, liquid mixtures, or oxidized species depending on local chemistry. Heat complicates glamour quickly. There is something charmingly human about hearing "diamond planet" and forgetting the lava. Now, why did later scientists become more cautious? Because astronomy improves, measurements get refined, methods sharpen. Earlier estimates of the host star's carbon abundance were revisited. Some later studies suggested the star may not be as carbon-rich as initially thought. If the star's composition is different, then assumptions about the planet's formation materials may also change. This does not mean the original scientists were careless. It means science is iterative. You work with the best available data, propose interpretations, then revise as better evidence arrives. That is not failure. That is the system functioning correctly. It is also less dramatic than social media would prefer. As a result, the certainty of calling 55 Cancri a diamond world has softened. Today, many researchers would phrase things more carefully. The planet may contain carbon-rich materials. It may have some diamond in its interior. It may instead be more Earth-like in broad composition but altered by heat and pressure. It may contain mixed layers we have not fully modelled yet. Reality often prefers mixed answers. Still, the nickname persists because it captures attention and because there is enough scientific basis to keep the idea alive as a possibility. And to be fair, 55 Cancri, a thermally extreme super-Earth, with composition still under active investigation, does not move as many clicks. Let us imagine for a moment what internal diamond layers would actually mean. Deep below any molten surface and hostile sky, carbon-rich material under crushing pressure could crystallize into vast masses of diamond-bearing rock. Not transparent jewel-store gems neatly cut by cosmic artisans, but dense geological diamond mixed with other minerals and defects. Dark, impure, fractured, perhaps conductive under conditions unlike anything in display cases. Planetary diamonds would be less romance and more mineral physics. The economics are also worth laughing at softly. Whenever rare materials are mentioned in space, someone asks what they would be worth. But worth depends on scarcity, extraction cost, transport, and market conditions. If humanity somehow imported a planet's worth of diamond, the price would likely collapse long before the first cargo arrived. Also, transporting lava-adjacent gemstones from 41 light-years away presents scheduling challenges. So, no, 55 Cancri is unlikely to solve household budgets. More importantly, the story teaches us that planets are products of chemistry plus environment. Change the ingredients slightly, and whole categories of worlds become possible. Carbon-rich worlds. Water worlds with global oceans hundreds of kilometers deep. Iron-heavy planets stripped of mantles. Worlds with atmospheres of hydrogen over rocky cores. Planets where rock rains from clouds. Our solar system is informative, but not exhaustive. That realization has transformed astronomy in the last few decades. Before exoplanet discoveries, theories were shaped mainly by our own local example. Then observations began revealing hot Jupiters, mini-Neptunes, ultra-short-period rocky worlds, and systems packed tightly with planets unlike anything nearby. Nature had been running a much larger experiment than we realized. 55 Cancri became one of the celebrity participants. There is another reason scientists cared about the diamond hypothesis. Composition influences everything else. A carbon-rich mantle conducts heat differently. Mineral phases affect tectonics, volcanic behavior, density, and atmospheric outgassing. If a planet's deep interior differs substantially from Earth's, then its surface story changes too. Even without jewelry metaphors, composition is destiny. Suppose the planet truly formed with abundant carbides and carbon layers. As it heated near its star, differentiated internally, and evolved over billions of years, those materials might interact in unfamiliar ways. Volcanism could release unusual gases, crustal behavior might differ, thermal conductivity may alter cooling rates, magnetic field generation could change depending on the internal structure. So Diamond Planet was never just sparkle. It was shorthand for potentially different planetary geology. Now let us gently dismantle one more misconception, that diamond automatically means beautiful. Beauty depends on context. A polished diamond under soft light is lovely. Diamond buried beneath megabars of pressure inside a furnace world is scientifically exciting, but less suited to necklaces. The universe is under no obligation to make valuable things aesthetically convenient. Indeed, many of the most interesting materials in planetary science exist in forms no one would wear, display, or recognize. If you somehow sliced 55 Cancri E open like an educational diagram, you might see layered structures shaped by gravity, perhaps a crust or magma shell, mantle zones, compressed interior phases, metallic core regions, and somewhere within, carbon transformed into dense crystal structures. But the actual cross-section is almost certainly more complicated than neat textbook layers. Planets are messy, evolving objects. Even Earth, which we know comparatively well, still holds surprises deep below. What I like most about this nickname is that it reveals something about human imagination. We encounter a hostile, scorching, distant super-Earth, and our first instinct is to ask whether it contains treasure. That is wonderfully on brand for our species, yet the real treasure is knowledge. Because through studying 55 Cancri E, astronomers refine methods for estimating mass and radius, model interior compositions, test atmospheric observations, compare planetary formation theories, and learn how rocky worlds behave under intense irradiation. The actual value lies not in gemstones but in understanding. And understanding tends to appreciate over time. There is also comfort in remembering that not all riches glitter. Earth's atmosphere is more valuable to us than diamonds. Fresh water outranks carbon crystals by any sensible standard. Temperate climate, fertile soil, stable oceans, and breathable air would be priceless almost anywhere else. A planet may hide diamonds while lacking rain. I know which world I would rather keep. The next time you hear Diamond Planet, it may help to translate the phrase into something truer. It means, here is a world whose chemistry may differ from ours. Here is a planet massive enough for extraordinary internal pressures. Here is a place where carbon could take unfamiliar forms. Here is evidence that rocky planets come in more varieties than we once assumed. That version is less flashy, perhaps, but far more interesting. Far beneath any glowing surface that 55 Cancri may possess. Below possible lava plains, below fractured crust, below regions where heat dominates everything we can easily imagine, there is another world entirely. It cannot be seen directly. No telescope peers neatly through layers of rock and magma to photograph it. No probe has descended there carrying a cheerful camera and unreasonable optimism. Yet science gives us strong reason to believe that the deep interior of this planet is a place where matter behaves in extraordinary ways. The surface of a planet often gets the attention because it is easier to picture. Mountains, oceans, clouds, deserts, volcanoes. These are familiar categories. Interiors are more difficult because they are hidden, compressed, and governed by physics that rarely enters daily conversation. But if we want to understand why 55 Cancri earned its famous nickname, or why scientists became so interested in its composition at all, we need to travel inward in thought. As depth increases inside any large rocky world, pressure rises dramatically. The weight of overlying material pushes downward from every direction. On Earth, this pressure becomes immense, even a few tens of kilometers below the crust. Far deeper, in the mantle and core, conditions are so extreme that common minerals transform into denser structures. Rocks do not remain what they were near the surface. They reorganize. That is one of the quiet truths of geology. Matter changes identity when the environment demands it. Now consider a planet more massive than Earth, packed into a relatively compact size, with stronger gravity compressing every internal layer. The deeper regions of 55 Cancri may experience pressures far beyond those found in Earth's mantle. Add high internal temperatures left over from formation, radioactive decay, tidal heating, and long-term thermal evolution. And you have a laboratory where atoms are pushed into new arrangements for billions of years. This is where the possibility of crystals becomes scientifically interesting. When most people hear the word crystal, they imagine decorative objects, clean edges, perhaps something sitting on a shelf catching sunlight. In planetary science, crystals are not ornaments, they are structures. Atoms arranged in repeating patterns according to chemistry and conditions. Salt forms crystals. Ice forms crystals. Quartz forms crystals. Diamond is a crystal. Many deep planetary minerals are crystals invisible to ordinary life. The universe is full of crystals that no one will ever wear. If 55 Cancri contains significant carbon, then under sufficient pressure and temperature, carbon may adopt dense crystal forms such as diamond. That is the origin of much public fascination. But even if carbon content is lower than early estimates suggested, high-pressure crystal phases of many materials are still expected inside the planet. Silicates, oxides, metallic alloys, exotic mineral structures all become possible. So the deeper truth is broader than Diamond Planet. It is a crystal planet in the sense that compressed interiors of rocky worlds are often dominated by crystalline solids shaped by extreme conditions. Let us begin with pressure itself. Pressure increases because each deeper layer must support the weight above it. On Earth, standing at sea level, we feel atmospheric pressure. Dive into the ocean and water pressure rises. Go into rock, and pressure becomes much larger still. At the centre of a planet several Earth masses in size, the values become staggering. Human intuition stops being useful somewhere along the way. Imagine stacking mountains on top of mountains until every grain below is squeezed from all directions. Then continue for thousands of kilometres. That begins to hint at planetary interiors. Under such stress, atoms are forced closer together. Empty space between them shrinks. Bonds rearrange into more efficient packing patterns. Minerals that are stable near a surface become unstable and convert into denser forms. This happens inside Earth, with olivine transforming into higher pressure phases deeper in the mantle. It would happen even more dramatically inside larger super-Earths. Heat complicates the picture in useful ways. High temperatures can melt materials, soften crystal lattices, speed chemical reactions, and allow atoms to migrate into new structures. Too much heat in one region may create molten layers. Elsewhere, pressure may keep materials solid despite enormous temperatures, because compression raises melting points for some substances. So deep interiors are not simply hot means liquid. They are balances between pressure and temperature. That balance creates layered complexity. A planet like 55 Cancri may possess outer molten zones due to stellar heating and internal heat, then deeper solid high-pressure mantles, perhaps partially molten transition regions, and an even denser metallic core. If carbon-rich enough, some internal bands could host diamond or related carbon phases. If not, other crystals take center stage. Either way, crystals are not decorative extras. They may be the skeleton of the planet. Now let us talk specifically about carbon. Carbon is remarkably flexible as an element. It forms graphite, diamond, soot, carbonates, organic molecules, graphene-like sheets, carbides with metals, and more. Near Earth's surface, graphite can be stable under some conditions. Under high pressure, diamond becomes favoured. That means the same element can express itself differently depending on environment. This versatility is one reason life uses carbon. It is also why planetary scientists pay attention to it. If large amounts of carbon were incorporated during formation of 55 Cancri, then as the planet differentiated and compressed, some carbon may have sunk or mixed into mantle regions where pressure transformed it. Over billions of years, extensive crystalline carbon layers could theoretically form. Not clear gemstones in neat rows, but vast masses of diamond-bearing material embedded in a planetary interior. There is something delightful about that contrast. The same substance sold in tiny rings on Earth may exist by the cubic kilometre elsewhere, hidden in darkness where no one can admire it. Yet diamonds would not remain untouched forever. High temperatures may destabilise some forms in certain regions. Chemical reactions with surrounding materials could convert carbon into other compounds. Convective motions may transport matter between layers. Impacts and resurfacing could disturb upper zones. Planets are not museum displays, they are active systems. This is why certainty remains difficult. We estimate mass and radius of 55 Cancri through astronomical observations. Those values give average density. Density narrows possibilities, but many different interior mixtures can produce similar totals. A world with more iron and less silicate might resemble another with different carbon content in bulk density terms. Add uncertain atmospheric layers and thermal expansion, and multiple models remain plausible. So when scientists discuss crystals inside 55 Cancri E, they're using evidence plus physics, not opening a hatch and checking directly. That is worth respecting. Planetary science often works like solving a locked box puzzle with only weight, size, and heat leaking through the seams. Now consider what such deep crystal layers might mean for geology. Crystal structure influences conductivity, viscosity, density, and how heat moves outward. If mantle materials conduct heat efficiently, the planet may cool differently than Earth. If some layers are rigid while others deform slowly, convection patterns change. Convection drives volcanism, crust recycling, and long-term thermal evolution. Thus, microscopic atomic arrangements can shape global landscapes. A crystal deep inside a planet may help determine whether volcanoes erupt on the surface. That sentence sounds absurd until one remembers how connected physical systems are. There's also the possibility of metallic crystals in the core. Many rocky planets likely host iron-rich cores, perhaps mixed with nickel and lighter elements. Under immense pressure, metals adopt structures unfamiliar at room conditions. Core crystallization can release heat and buoyancy, potentially powering magnetic dynamos. Whether 55 Cancri E has a sustained magnetic field remains uncertain, but interior phase changes matter greatly. Magnetic fields in turn influence atmospheric retention by deflecting stellar particles. Suddenly, our journey from crystals to sky protection seems less indirect than expected. Pressure can also create materials Earth barely knows. Laboratory physics routinely discovers new high-pressure phases that exist only under intense compression. Super-Earth interiors may naturally host minerals we have not fully characterized. Their names may someday be technical and difficult to pronounce, ensuring scientific tradition continues smoothly. This means 55 Cancri E may contain matter that no human has ever held in stable form. There is something thrillingly humbling in that. The periodic table is shared across the cosmos, but the combinations and structures available under alien conditions are far richer than surface Earth experience suggests. Now imagine descending inward through the planet, protected by impossible technology and narrative generosity. First comes a scorched crust, perhaps fractured and partially molten. Deeper, hotter rock under pressure flows slowly over long timescales like thick putty despite being solid. Farther down, crystals pack tighter, minerals transform, density rises. Carbon-rich zones, if present, harden into diamond-bearing layers. Lower still, metals compress into a core where heat and pressure erase all household comparisons. There would be no caverns glittering theatrically, no hidden palace walls of polished gem. Real planetary interiors are denser, darker, rougher, and far more impressive than fantasy architecture. Because the true wonder is not appearance, it is process. Atoms responding to gravity over billions of years, layers sorting themselves, heat trying to escape, pressure rewriting chemistry, a whole planet slowly negotiating with the laws of physics. That same story happened here on Earth, only under different terms. Our continents float because mantle convection moves beneath them. Our magnetic field likely depends on core dynamics. Diamonds formed in deep mantle settings and were later delivered upward. Volcanoes release gases that help shape atmosphere. Interiors matter even when unseen. Studying 55 Cancri reminds us that surface beauty is only one chapter of a planet's biography. Most of the story is buried. There is another philosophical comfort hidden in this science. Pressure does not only destroy, it also creates order. Under enough compression, carbon becomes diamond. Under enough time, chaos can become structure. Conditions that seem harsh may produce remarkable forms. Not every pressure leads to something useful, of course. Sometimes it just ruins lunch. But in planetary terms, extremes often generate complexity. The nickname Diamond Planet survives because it is vivid, but perhaps World of Transformed Matter would be truer. It lacks sparkle, admittedly, yet it captures the deeper lesson. Planets are machines for changing materials. Here on Earth we use pressure in modest ways. We compress coal into briquettes, forge steel, form ceramics, polish gems. Nature does the same at scales that make our factories look like toy workshops. Entire mantles become presses. Whole worlds become furnaces. And all of this may be happening right now, 41 light-years away, while you sit in ordinary gravity under a breathable sky on a crust cool enough to support furniture. That contrast can make everyday life feel wonderfully fortunate. Time feels dependable because Earth trained us that way. Morning arrives, afternoon follows, evening softens the sky, and night settles in with predictable patience. We organise work, meals, sleep, holidays, birthdays, and mild existential concerns around a rotating planet that takes roughly 24 hours to complete one turn. That rhythm becomes so familiar that we mistake it for normal rather than local. Then a planet like 55 Cancri E appears and reminds us that clocks are provincial. On this distant world, a full orbit around its star takes less than one Earth day. Roughly every 18 hours, the planet completes an entire year. Seasons, if one could use that word there at all, would have no time to unpack. Anniversaries would arrive before laundry finished drying. Tax deadlines would be emotionally relentless. When astronomers first discovered ultra-short-period planets like this, it challenged intuition. We were accustomed to our own solar system, where Mercury, the innermost planet, still takes 88 Earth days to circle the Sun. Even Mercury, fast and sun-baked by our standards, would seem leisurely compared with 55 Cancri E. This world races. To understand how remarkable that is, imagine the scale involved. Planets move faster when they orbit closer to their stars because gravity is stronger there. The closer you are, the tighter the curve, and the greater the speed needed to remain in orbit rather than falling inward. It is the same principle that makes inner planets in our solar system move faster than outer ones. Mercury outruns Neptune by a wide margin. 55 Cancri takes the concept and commits fully. Its orbit is so close that the star dominates its sky, and the planet whips around in a matter of hours. While you sleep one ordinary Earth night, this world may have completed most of another year. Now, we should pause and separate two ideas humans often blend together: a day and a year. On Earth, a day is one rotation of the planet on its axis. A year is one orbit around the Sun. Those two numbers happen to coexist in a comfortable arrangement: 24 hours for a rotation, 365 days for an orbit. Because we grew up here, this feels sensible. Elsewhere, there is no requirement for such convenience. A planet may rotate slowly and orbit quickly. It may rotate quickly and orbit slowly. It may be tidally locked so that one rotation matches one orbit. It may spin backward, wobble dramatically, or resonate in unusual ratios. The universe did not consult calendar makers. For 55 Cancri E, evidence suggests the planet is likely tidally locked or close to it, due to intense gravitational interaction with its star. If so, the same side may always face the star. That means the familiar Earth concept of sunrise and sunset may disappear across much of the planet. This creates a delightful complication. If one side always faces the star, then what exactly counts as a day there? From an orbital standpoint, the planet's year is about 18 hours. From a surface observer on the star-facing side, the star may barely move in the sky at all. Noon becomes permanent. From the dark side, midnight is eternal. In practical terms, day stops meaning a light-dark cycle and becomes an orbital technicality. This is a useful reminder that many words we use casually are tied to Earth's circumstances. Daylight, month, year, season, even weather patterns. Move elsewhere, and language must stretch. Suppose you lived on 55 Cancri with impossible protective technology and an admirable willingness to ignore danger. Birthdays would arrive more than once daily by Earth standards. A child could turn 10 in under a week. Midlife crises would need scheduling software. Yet age itself would still be biological, not orbital. You would not mature faster simply because the planet circles quickly. This distinction matters. Timekeeping systems are labels placed on motion. Bodies follow chemistry and physics, not birthday cake frequency. Still, social life would be entertaining. Happy 30th birthday. Thank you. I feel overheated. The speed of orbit also affects the planet's environment. Close-in planets receive intense radiation, strong tidal forces, and gravitational shaping from the host star. Orbital mechanics is not just about how long a year lasts. It helps determine geology, atmospheric escape, rotation state, and long-term stability. Fast years come with consequences. Because the orbit is so tight, the planet likely became tidally locked over time. Tidal locking occurs when gravitational forces raise bulges in a planet, dissipate energy internally, and gradually synchronize rotation with orbit. Our moon did this with Earth. 55 Cancri likely did it with its star far more dramatically, because proximity accelerates the process. Thus, the short year and the locked rotation are related chapters of the same story. Closeness to the star. Now let us imagine what the sky might feel like if the planet were not perfectly locked, but in some near-synchronous state. The star could drift slowly, perhaps tracing small motions over long intervals. Tiny changes in heating might shift atmospheric flows or surface temperatures. Even subtle orbital eccentricity could matter because close worlds live under magnified conditions. Small differences become large outcomes when the furnace is nearby. There is another strange consequence of short orbital periods: repeated transits. If the planet passes in front of its star from our line of sight, astronomers get many opportunities to observe it, compared with worlds that orbit once every year or once every decade. Every transit slightly dims the star's light. Measure those dips repeatedly, and scientists refine size, orbit, timing, and atmospheric clues. So while life on such a world would be dreadful for humans, it is wonderfully convenient for telescopes. This is one reason planets like 55 Cancri attract so much scientific attention. They keep showing up on schedule. A planet with a 1-year orbit gives one transit chance annually if geometry is right. A planet with an 18-hour orbit gives frequent opportunities. Nature, having made the planet inhospitable, at least made it punctual. There is also the matter of speed itself. Orbital velocity that close to a star is immense. The planet is not strolling through space. It is racing around its sun at tremendous speed, held in a continuous free-fall curve. Yet from the planet's own frame of reference, nothing feels like motion in the everyday sense. This is another useful cosmic lesson. Constant motion often feels like stillness when everything moves together. Earth demonstrates the same thing. We orbit the Sun at about 30 kilometers per second, rotate at hundreds of meters per second depending on latitude, and travel through the galaxy as well. Yet your tea usually remains in the cup. Motion is often invisible from inside the system experiencing it. Let us compare this with Mercury for perspective. Mercury's year lasts 88 Earth days, and its rotation is locked in a 3:2 resonance with the Sun, rotating 3 times every 2 orbits. Already that is strange by human standards, yet 55 Cancri circles in less than 1 Earth day. If Mercury is unusual, 55 Cancri is the friend Mercury warns you about. What would calendars look like there? If local civilization somehow existed in defiance of every known comfort, they would probably abandon orbit-based years quickly. A practical society on a tidally locked furnace world might measure time through internal clocks, geological cycles, energy quotas, maintenance intervals, or star spot patterns. When years are shorter than sleep cycles, tradition must improvise. Even human astronauts in space already rely on artificial schedules because orbital sunrises can happen every 90 minutes aboard low Earth orbit stations. Biology needs rhythm more than astronomy provides it. That point brings us back to ourselves. Our circadian rhythms evolved under 24-hour light cycles. Hormones, temperature regulation, alertness patterns, sleep timing, digestion, and mood all carry traces of Earth's rotation. Place humans on a world with no meaningful sunrise and sunset, and we would need clocks and carefully designed routines to preserve health. 55 Cancri would be a spectacular place to fail at jet lag permanently. But beyond physiology, there is something philosophically calming here. We often treat our measures of time as universal truths: hours, days, weekends, late nights, early mornings. Yet these are local agreements built atop one spinning planet. Elsewhere, a year is 18 hours. Elsewhere, a day may not exist in familiar form. Elsewhere, dawn never comes. This can loosen the grip of rigid schedules just a little. Your missed appointment today mattered in context, yes, but context is everything. Cosmic timekeeping is gloriously inconsistent. Somewhere an entire calendar has already passed while you search for your keys. The star system itself is older than Earth by billions of years, yet one of its planets counts years faster than we count shifts at work. Long history and short cycles coexist easily in nature. There is wisdom in that contradiction. Now imagine watching the planet from orbit. Below, a glowing hemisphere faces the star. In less than a day, the world completes another lap. Data streams into instruments. Thermal signatures shift. Another year passes, and another, and another. While deep inside, crystals may compress, magma may circulate, and the surface may churn almost indifferent to the frantic orbital pace. Fast calendars do not mean hurried geology. Many processes there still unfold slowly. Mantle convection, crustal recycling, atmospheric loss, tidal evolution. The clock of orbit is rapid. The clock of planetary change can remain patient. This mirrors life more than it first appears. Some days race by while deeper transformations take years. There is comfort in knowing even extreme worlds contain multiple tempos. For scientists, short periods also help test gravitational interactions with neighbouring planets. Tiny timing variations in repeated orbits can hint at additional bodies, mass estimates, and dynamical relationships in the wider system. The planet becomes not only a world, but a clockwork component in a larger celestial machine. Except this clockwork component may have lava seas and a hostile sky, which makes it more memorable than standard gears. If you glance at a household clock tonight, it may feel a little more charmingly arbitrary. 24 equal slices around a dial because our planet spins once in roughly that interval. Another world could justify 18-hour days, or permanent noon, or centuries-long winters. The universe offers no preferred clock face. Standing up feels effortless only because Earth made it seem ordinary. We rise from chairs, walk across rooms, climb stairs reluctantly, lift bags we should have packed more wisely, and rarely pause to thank gravity for being strong enough to keep oceans attached yet gentle enough to allow knees some dignity. Our bodies evolved here. bones, muscles, circulation, balance, posture, even the casual act of reaching for a cup, all assume Earth's pull as background truth. Then astronomy introduces a world like 55 Cancri and reminds us that even something as basic as standing has local rules. This planet is larger than Earth and substantially more massive. Current estimates place it at roughly twice Earth's diameter and several times Earth's mass. Those numbers matter because gravity at a planet's surface depends primarily on mass and radius. More mass pulls harder. Greater radius increases distance from the centre and can soften the effect somewhat. Combine both, and you get a world where surface gravity is likely significantly stronger than what we experience at home. In simpler terms, if you visited 55 Cancri, everything you carry would feel heavier, including yourself. Of course, the lava, toxic sky, and surface temperatures would remain the more immediate concerns. But let us set those aside for a moment and focus on weight. Weight is not the same as mass. Your mass, the amount of matter in your body, stays the same wherever you go. Your weight changes depending on gravity. On the Moon, you weigh less because lunar gravity is weaker. On Jupiter, if one could stand on a suitable platform and ignore many practical problems, you would weigh more because its gravity is stronger. On 55 Cancri, you would likely feel noticeably heavier than on Earth. If surface gravity were roughly twice Earth's, a person who feels comfortable walking here might feel burdened there. Legs would work harder, joints would complain earlier, getting up from the ground would become an athletic event, running would be inefficient, jumping would lose its charm quickly. There is something amusing about how often science fiction imagines alien travel while forgetting staircases. Now, why is this planet so dense and massive? Because it is a super-Earth, a category of planets larger than Earth but smaller than ice giants like Neptune. These worlds can have a variety of compositions. Some may be rocky with iron cores and silicate mantles. Some may contain thick volatile layers or deep oceans under high pressure. Others may blur categories entirely. 55 Cancri appears dense enough to suggest a substantial rocky component rather than being a puffed-up gas-draped world. That density hints at strong internal compression. The planet's own gravity squeezes it inward, increasing pressure toward the centre. This is one reason its interior may host exotic mineral phases, and perhaps carbon transformed into dense crystal forms. Gravity does not merely hold you down. It shapes the inside of worlds. There is a tendency to think of gravity as simple downward force. In reality, gravity is architecture. It determines whether a planet retains an atmosphere, how tall mountains can grow, how magma moves, whether oceans stay liquid under pressure, how satellites orbit, how tides flex crusts, and how planetary layers separate over time. It is one of the great sculptors of worlds. Let us imagine stepping onto 55 Cancri with impossible protective equipment and an insurance policy signed by several lawyers. The first sensation might be weight in the chest and legs, not crushing instantly, but insistent. Your body would feel denser to yourself, as though every movement required extra agreement from muscles. Standing upright would consume more effort. Walking a few meters might resemble carrying groceries uphill after a long day. Arms would tire faster. Lifting tools would become labour. If you dropped something, bending to retrieve it would feel like negotiating with physics. And remember, this is before accounting for heat that could melt rock. Astronauts train in altered gravity because even small changes matter. In microgravity, muscles weaken and bones lose density without countermeasures. In stronger gravity, the opposite challenge emerges. The body must constantly support more load. Over time, circulation can strain, locomotion becomes costly, and fatigue arrives early. Humans are adaptable, but we're not infinitely adaptable. If a child somehow grew up in higher gravity from birth, development might differ. Stronger bones and muscles could be favoured if biology could cope. Height might be reduced, cardiovascular demands would increase, daily life would shape architecture too, chairs lower, ceilings less relevant, jumping games unpopular. Yet on 55 Cancri E, environmental hostility likely prevents any such thought experiment from becoming practical. Still, gravity alone is enough to imagine another style of civilization somewhere else, on another kinda high-gravity world. That is one of the joys of comparative planetology. Even when one world is unlivable, it teaches principles useful elsewhere. Now consider movement of air and liquids under stronger gravity. Atmospheres can become more tightly bound to the planet, all else equal. Scale height, the vertical extent over which atmospheric pressure drops, decreases with stronger gravity if temperature and composition are similar. In everyday language, the atmosphere may hug the surface more closely. Mountains would interact with weather differently, convection patterns shift. Falling particles settle differently. Liquids too feel gravity. Waves move under restoring forces influenced partly by gravity. Lava on 55 Cancri E, if present in broad seas or flows, would spread and pool under stronger pull. Volcanic plumes might arc differently than on Earth. Eruptions launching material upward would fight a heavier leash. Even mountains have limits set by gravity. A planet with stronger gravity tends to flatten tall topography, because rock under its own weight flows or fractures when structures become too high. On Earth, Everest reaches nearly 9 kilometers above sea level. On a much stronger gravity world, similarly tall, unsupported mountains become hard to sustain depending on crust strength and tectonics. So landscapes there may favour broader rises, shorter peaks, or constantly recycled terrain rather than dramatic needle-like summits. Gravity edits scenery. There is also the matter of tides. Because 55 Cancri orbits very close to its star, tidal forces from the star are intense. These forces stretch the planet slightly, creating internal friction and heat if the shape changes over time. We discussed tidal locking earlier, but gravity remains central to that story. The star's pull may have synchronized rotation and could continue stressing the interior. Thus, gravity is not only what you feel at the surface, it is what needs the whole planet. This brings us to a subtle but lovely truth. Every world has a personality partly written in acceleration. The Moon invites bounding steps. Mars offers lighter walking and towering volcanoes, partly because gravity is weaker. Jupiter's large moons vary in pull enough to change how ice behaves. Small asteroids barely hold onto dust. 55 Cancri likely asks every object to stay closer, press harder, and move more deliberately. Even falling looks different. Drop a stone there and it accelerates faster downward. Toss something upward and it returns sooner. Projectiles travel shorter, graceful arcs. Sports would be reimagined immediately or abandoned for board games. Now, because the planet is larger than Earth, the horizon from standing height might appear slightly farther away depending on exact radius. Yet the heavier pull would dominate bodily experience more than visual geometry. You might notice the strain before admiring the view, if there were any safe view to admire. Strong gravity also influences atmosphere loss indirectly. A more massive rocky planet can hold onto heavier gases more effectively than a smaller one, though extreme stellar radiation may still strip lighter molecules or energize escape processes. This balance matters greatly for close-in planets like 55 Cancri E. The planet's gravity says stay, while the nearby star says leave. Planetary history often emerges from such arguments. Could humans adapt temporarily with technology? Perhaps exoskeletons, pressure suits, support systems, and medical preparation could help on some high-gravity worlds. But long-term residence in much stronger gravity remains biologically challenging. Bones, discs, joints, and hearts would all register formal complaints. Thankfully, Earth remains pleasantly moderate. This is easy to overlook. We complain about carrying boxes upstairs, yet we inhabit a gravity regime that permits birds, trees, mountain climbing, basketball dancing, and naps on couches without compression injuries. That is a rather elegant compromise. Learning about heavier worlds can restore appreciation for ordinary steps across ordinary floors. There is another emotional comfort here. Weight itself is relative. What feels burdensome on one world may feel manageable on another. Context shapes effort. Even in life, burdens are often measured against the gravity around us. A cosmic metaphor, yes, but a practical one too. If you watched 55 Cancri from orbit, gravity's effects would be invisible yet everywhere. It holds the planet together against rotation. It organises dense materials inward and lighter materials outward. It binds atmosphere if any remains. It shapes lava seas, crust thickness, core pressure, and the path of every particle trying to escape. Invisible forces often do the most work. Our own world proves the same. Gravity never asks for applause. It simply keeps rivers flowing, feet grounded, moons orbiting, and furniture honest. On 55 Cancri, that same force speaks in a firmer voice. Not every planetary story is really about the planet. Sometimes the central character is the star. Worlds do not choose their climates, their day lengths, their atmospheric struggles, or the amount of energy pouring onto every stone. These conditions are assigned by orbital distance, stellar brightness, age, radiation, magnetic behavior, and the long history of formation. A planet may have mountains and lava and gravity of its own, but the star often writes the first draft of everything else. That is especially true for 55 Cancri A. To understand why this world may host molten surfaces, possible rock vapour skies, intense tides, and a year shorter than one Earth day, we must look at the object it circles, the star known as 55 Cancri. Its name is functional rather than dramatic. Many stars were catalogued before anyone suspected they might host remarkable planets, so they received labels instead of poetry. Yet behind that tidy designation is a real sun, shining dozens of trillions of kilometres away, old enough to have seen ages pass, steady enough to anchor multiple planets, and close enough to one particular world to make it nearly unrecognisable. 55 Cancri is often described as a sun-like star. That is broadly true, though like many family comparisons, the details matter. It is a G-type main sequence star, similar in general category to our Sun, but somewhat smaller, cooler, and less luminous. Think of it not as our Sun's twin, but as a slightly different sibling with a calmer surface personality and a very dramatic inner planetary arrangement. Because stars can differ modestly in mass and brightness while producing radically different planetary environments depending on orbital spacing. This is one of the easiest facts to forget. A planet's temperature depends not only on what kind of star it orbits, but how close it dares to go. Earth receives a comfortable amount of solar energy because we orbit at about 1 astronomical unit, the average Earth-Sun distance. Venus, only modestly closer, receives much more and became a greenhouse furnace. Mercury, closer still, endures intense heating and lacks a thick atmosphere to moderate extremes. 55 Cancri orbits vastly closer to its star than Earth does to ours. That closeness changes everything. Even if 55 Cancri is somewhat dimmer than the Sun, distance dominates the equation. Stand close enough to a campfire and the difference between medium and large stops mattering quickly. The planet receives enormous stellar radiation simply because it is almost pressed against the source compared with our standards. This is why a star that is not outrageously hot can still produce a world of lava oceans. The relationship between star and planet is intimate in the most gravitational sense. 55 Cancri completes an orbit in about 18 hours. Imagine a world circling its sun so quickly that by the time you've prepared breakfast, another year is nearly underway. Such speed only happens near the star, where gravity is strong and orbital paths are tight. From the surface, if one could somehow survive long enough to observe, the star would appear huge in the sky, compared with how our Sun appears from Earth. Not because it is larger in absolute size than our Sun, but because the planet is so close. Angular size matters to experience. A nearby lamp feels brighter than a distant chandelier. The sky there may be dominated by a blazing stellar disk that never grants personal space, and if the planet is tidally locked, as many scientists suspect, one hemisphere may face that star continuously. No sunset, no cool evening, no mercy through rotation. The same side receives constant radiation day after day, year after year, while the opposite hemisphere remains in darkness. That means the star is not just a source of daylight, it is an environmental pressure applied without pause. Stars also emit more than visible light. They produce infrared radiation, ultraviolet light, stellar winds, charged particles, magnetic disturbances, and occasional activity depending on their temperament and age. Even a relatively stable star influences nearby planets through a full spectrum of energy. At close range, these effects become serious. Ultraviolet radiation can break apart molecules in upper atmospheres. Lighter gases may then escape to space. Charged particles can erode atmospheric layers if magnetic shielding is weak. Heat drives expansion of atmospheric gases, making loss easier. Over long time scales, the star can strip, transform, or repeatedly reshape what a planet tries to keep. So when we ask whether 55 Cancri has an atmosphere, we are partly asking how well it has survived its relationship with the star. Some worlds are blessed with distance, others endure intimacy. Now let us talk age, because age matters in stars. 55 Cancri is believed to be older than our Sun, likely several billion years old. Older stars often change slowly in luminosity and activity over time. During its youth, it may have been more magnetically active, with stronger stellar winds and higher radiation output. If so, the early life of 55 Cancri could have been even harsher than today. Imagine a world already too close, then add a younger, more energetic star. That early phase may have stripped volatiles, altered chemistry, reshaped crust, or driven atmospheric escape more aggressively. What we see now may be the survivor version of a longer history. Planets are biographies, not snapshots. There is also the question of migration. Did 55 Cancri form near the star, or farther away and move inward over time? Many planetary systems show evidence that worlds do not stay where they begin. Giant planets can migrate through disks of gas. Smaller rocky bodies may shift due to gravitational interactions. If 55 Cancri formed farther out, where temperatures were lower, it may once have contained more volatiles or different materials before spiraling inward to its current scorched orbit. That possibility makes the star's role even more dramatic. It may not only heat the planet now, it may have transformed a once different world into the furnace we infer today. A calm-seeming star can still be the author of great upheaval. One useful comparison is our own Sun. We often think of it as gentle because we know how to live under it. Yet even here, solar storms disrupt satellites, auroras bloom from magnetic interactions, and long-term solar brightening will eventually render Earth uninhabitable billions of years from now. Stars are generous and dangerous at once. Place yourself much closer to one, and the dangerous part becomes harder to ignore. If telescopes observe changing thermal signatures from 55 Cancri, the star remains part of the explanation. Constant irradiation interacts with surface magma, atmospheric circulation, possible clouds of vaporized minerals, and heat transport from dayside to nightside. The star does not merely shine on the system, it actively drives weather and geology from afar. In that sense, stars are remote-controlled devices for planets. Now imagine standing once again impossibly protected on the day side of 55 Cancri. Above you hangs a brilliant star, larger than our Sun appears from Earth, fixed in place, or nearly so. The sky glows with heat haze. Shadows are sharp. The ground radiates warmth upward with hostile enthusiasm. The star does not travel westward. It does not promise evening. It simply remains. There is something psychologically intense about a sun that never sets. Humans evolved under cycles. Morning energizes, sunset relaxes, Darkness signals rest. Remove that pattern and time itself feels altered. On a tidally locked close-in world, the star becomes less a clock and more a constant command. Keep heating. Yet for all its severity, 55 Cancri itself is not malicious. It is doing what stars do, fusing hydrogen into helium, releasing energy, shining according to mass and composition. The cruelty is accidental geometry. This is an important cosmic lesson. Many harsh environments are not caused by violence, but by ordinary processes in unfortunate combinations. A normal star plus a too close orbit equals extraordinary consequences. There is beauty in the star too. From a distance of 41 light-years, its light reaches our telescopes after crossing interstellar space, untouched by oceans, cities, forests, or weather. That light carries information, tiny wobbles revealing planets, subtle dips during transits, spectral fingerprints of chemistry, long records of brightness and motion. We learn about alien worlds by reading starlight with patience. Without the star, 55 Cancri would be invisible to us in practice. It shines mainly because it reflects and re-radiates stellar energy. Even our knowledge of the planet comes through the star's behaviour. The star hides it, reveals it, tugs on it, heats it, and helps us detect it. Parent star is not merely a title, it is structurally accurate. There is comfort in remembering that our own lives depend on similar generosity. The sun powers climate, photosynthesis, food webs, and weather. It also occasionally sunburns us and fades patio furniture. Relationships with stars are complicated. Earth simply enjoys a healthier boundary. This may be why exoplanet science often returns us to gratitude. A breathable sky, moderate sunlight, water that remains water, nights cool enough for sleep, seasons that mostly negotiate rather than attack. These are products of orbital distance and stellar temperament as much as anything else. We live beside a star that burns from far enough away. 55 Cancri E does not. For most of human history, planets beyond our solar system belong to imagination. They appeared in philosophy, poetry, religion, speculation, and hopeful conversation beneath night skies. People wondered whether other stars hosted worlds, but wondering and knowing are very different things. You can look at a star with naked eyes and feel curiosity immediately. What you cannot do so easily is see the small dark planets circling it. Stars are bright, planets are faint, distance is rude. That is why the discovery of worlds like 55 Cancri E is one of the quiet triumphs of modern science. We didn't find them by flying there, photographing them up close, or catching them politely introducing themselves. We found them by noticing tiny effects, slight signals and patterns so subtle that older generations would have considered them unreachable. This is the story of learning to detect the nearly invisible. The first thing to understand is that stars and planets do not behave the way simple diagrams sometimes suggest. In children's books, a star sits in the centre, while planets orbit neatly around it as if attached to invisible strings. In reality, both star and planet orbit their shared centre of mass. The star is far heavier, so it moves only a little, while the planet moves much more. But that little stellar motion can still be measured. Imagine a large person and a small dog tied together by a rope on slippery ice. The dog runs around excitedly. The larger person does not stay perfectly still. They wobble, shuffle, and get dragged into minor dignity issues. That stellar wobble became one of our greatest tools. The system containing 55 Cancri was first known as a star long before its planets were confirmed. Astronomers catalogued it, measured its brightness, tracked its position, and gradually learned its properties. Later, with more precise instruments, they began noticing periodic changes in the star's motion along our line of sight. How do we detect motion in a star dozens of trillions of kilometers away, through light? When an object moves toward us, its light shifts slightly toward shorter wavelengths. When it moves away, the light shifts toward longer wavelengths. This is the Doppler effect, the same principle behind the changing pitch of a passing siren. Sound stretches and compresses with motion. Light does something similar. By splitting starlight into a spectrum and measuring incredibly tiny shifts in spectral lines, astronomers can determine whether a star is moving toward or away from Earth by small amounts. If that motion repeats in a regular cycle, an orbiting planet may be tugging on it. This technique is called the radial velocity method. It is a magnificent example of patience. No one sees the planet directly. Instead, scientists observe a star quivering slightly because something unseen is pulling on it. It's rather like noticing a hidden dancer by watching the curtain move. The 55 Cancri system became one of the earlier known multi-planet systems discovered through this method. Over time, astronomers detected several planetary companions by analysing repeated signals in the star's motion. Each planet contributes its own gravitational tug, its own orbital rhythm, its own line in a complex symphony of data. Separating those signals is not simple. Imagine listening to an orchestra and trying to identify one violin, one clarinet, and one quietly ambitious triangle while standing outside the building. That is roughly the challenge. The existence of multiple planets around 55 Cancri made the system scientifically exciting. It also made analysis harder. Different orbital periods overlap. Long-period giants create slow trends. Short-period planets create quick repeating signals. Instrument precision matters. Stellar activity can imitate planetary signals if star spots or magnetic cycles alter spectra. Nature does not provide clean spreadsheets. 55 Cancri E, in particular, became famous partly because of how its signal was refined over time. Early interpretations of data suggested one orbital period, but later reanalysis corrected that picture and revealed a shorter period planet. This is another excellent lesson in science. Discovery is not always one dramatic moment. Sometimes it is years of measurements, rechecking assumptions, noticing aliases in data, and admitting that the earlier answer was close but not correct. The corrected period showed that 55 Cancri E circles its star in less than one Earth day. That changed everything. A planet whipping around its star every 18 hours is easier to observe repeatedly than one taking months or years. Frequent orbits mean many chances to confirm timing, improve models, and look for additional effects. It also immediately suggested an extreme environment, a world orbiting astonishingly close to its star. So first we sensed the tug, then we understood the pace, then we began imagining the heat. But the story did not end with radial velocity. Another powerful technique soon joined the effort, the transit method. If a planet's orbit is aligned just right from our viewpoint, it passes in front of its star and blocks a tiny fraction of starlight. The star dims very slightly and predictably. Measure those repeated dips and you can infer the planet's size, orbital period, and sometimes hints of atmosphere. This sounds straightforward until you consider the scale. A small planet crossing a star blocks only a tiny percentage of the light. It is equivalent to noticing a minor change in brightness from across interstellar distances, while also accounting for instrument noise, stellar variability, and the universe generally being unhelpful. Yet we learned to do it. 55 Cancri E was later observed to transit its star. That was a major milestone because combining transit data with radial velocity data is extremely valuable. Radial velocity gives you information about mass, though often a minimum mass depending on geometry. Transit data gives size, mass plus size gives density. Density is where imagination becomes geology. If a planet is large but light, it may be gaseous or water-rich. If it is compact and heavy, it may be rocky or metal-rich. 55 Cancri E appeared dense enough to belong in the rocky super-Earth category, immediately making its close orbit even more dramatic. A gas giant close to a star is strange but conceptually familiar. A rocky world with likely molten conditions captures attention differently. Now let's appreciate what super-Earth means operationally. It does not mean better than Earth. Despite what the name playfully suggests, it means a planet more massive than Earth, but still smaller than ice giants like Neptune. Our solar system oddly lacks this common galactic category, so exoplanet discoveries introduced us to worlds that are statistically common, but locally absent. 55 Cancri became one of the headline examples. With repeated transits, astronomers also measured thermal emission and brightness changes as the planet moved around its star. Infrared observations hinted at intense temperatures and possible day-night contrasts. Some data suggested variability over time, leading to theories about volcanic activity, changing atmosphere, or lava flows. Think about how astonishing that is. We first detect an invisible tug on a distant star, then we infer an orbiting planet, then we measure its size, then we estimate its mass, then we begin debating whether lava seas change its glow. This is not guesswork in the casual sense, it is inference stacked carefully on evidence. Modern astronomy often works by combining small truths until a larger truth emerges. Of course, there were disagreements and revisions along the way. Datasets improve, statistical methods improve, instruments become more sensitive, competing models are tested, some early claims become weaker, others strengthen. This is exactly how a healthy scientific field behaves. People sometimes imagine science as a collection of final answers. It is better understood as a disciplined process of reducing error. 55 Cancri benefited from that process repeatedly. The star itself also helps. Because 55 Cancri is relatively nearby in cosmic terms and bright enough for detailed study, observations are more practical than for dimmer, farther systems. Nearby stars are treasures to exoplanet hunters because every extra photon helps. Light is information, and telescopes are hungry readers. Let's imagine the practical reality behind these discoveries. Night after night, observatories gather starlight. Instruments calibrated with extraordinary care compare wavelengths to astonishing precision. Researchers process data, remove noise, account for weather, temperature drift, detector quirks, stellar behavior, and human error. Months become years. Papers are written, challenged, revised. New telescopes revisit old targets. Meanwhile, somewhere in the data, a world circles every 18 hours without knowing it has become famous. There is something deeply comforting about that image. The planet is simply being a planet. We are the ones attaching names, graphs, uncertainty bars, and fascination. This discovery story also reveals a human strength that deserves more admiration: indirect thinking. We could not see the planet clearly, so we asked what else it would affect. We noticed the star wobble. We noticed light dim. We measured timing. We inferred mass, size, density, and temperature. Intelligence often advances not by staring harder, but by noticing consequences. Many things in life are known this way: wind by moving leaves, emotion by tone of voice, gravity by falling cups, planets by trembling stars. There is also humility in remembering how recent this knowledge is. For nearly all of history, no one knew with certainty that 55 Cancri existed. Then, within a few decades, humans learned its orbit, approximate mass, radius, likely temperature extremes, and possible atmospheric puzzles. The night sky did not suddenly become richer. We simply learned to read it better. That pattern repeats across science. Reality often waits unchanged while understanding catches up. So when you hear that a distant lay of a world 41 light-years away has been discovered, it is worth hearing the hidden sentence beneath it. Humanity built tools delicate enough to detect tiny motions in ancient light, and patient enough to trust the numbers. That is a lovely achievement for a species that still occasionally misplaces its keys. Seeing is overrated, at least in astronomy. We often assume that to understand something we must look directly at it. We want clear photographs, close-up maps, dramatic footage, perhaps a helpful label floating nearby. That expectation comes from life on Earth, where most things worth knowing are near enough to inspect. If you wonder what kind of tree stands outside, you can walk over to it. If you want to know whether bread is burnt, a glance usually settles the matter. Planets 41 light-years away do not cooperate with such habits. 55 Cancri is not available for casual viewing through a backyard telescope. It does not present itself as a neat glowing marble beside its star. The star is far brighter, the distance immense, and the angular separation tiny. Direct imaging of such a close-in small planet is extraordinarily difficult. So astronomers do what they often do best. They become clever. Instead of demanding a portrait, they study consequences. Light, shadows, timing, tiny changes in brightness, subtle shifts in wavelength, repeating patterns, missing photons, extra heat. Each clue by itself may seem modest. Together they become evidence. This is how we learn about alien worlds we cannot yet visit. 55 Cancri is an excellent example, because so much of what we think we know about it comes not from seeing the planet directly, but from reading the traces it leaves in data. Let us begin with shadows. When the planet passes in front of its star from our point of view, it blocks a small fraction of starlight. This event is called a transit. The star dims slightly for a short time, then returns to normal brightness after the planet moves across. That dip in light may be tiny, but modern instruments can measure astonishingly small changes. Imagine noticing a fruit fly crossing a lighthouse beam from many kilometers away. The scale is different, but the spirit is similar. From the depth of that dimming, astronomers estimate the planet's size. A larger planet blocks more light. A smaller one blocks less. Repeated transits refine the radius measurement and confirm the orbital period. If the dip occurs every 18 hours or so, the world is reliably circling on schedule. That means a shadow becomes a ruler. Now let us add timing. If transits arrive exactly when expected, the orbit is stable and models behave well. If they arrive a little early or late, gravitational interactions with other planets may be tugging the orbit subtly. This method, called transit timing variation analysis, can reveal neighbouring worlds, mass relationships and orbital architecture, so a delayed shadow can betray an unseen companion. There is something charmingly detective-like about this. We're not catching planets red-handed. We're noticing that one planet is late and concluding that another must have interfered. Next comes colour, or more precisely, wavelength. When starlight passes through the edge of a planet's atmosphere during transit, some wavelengths may be absorbed more than others depending on atmospheric composition. Sodium absorbs particular wavelengths, water vapour others. Methane, carbon dioxide, hydrogen, and many other molecules each leave spectral fingerprints. For 55 Cancri, the challenge is formidable. The planet is small compared with giant gas worlds, and any atmosphere may be thin, variable, or difficult to interpret. Yet even attempting such measurements tells us how far astronomy has advanced. We are testing the chemistry of a distant sky using filtered starlight. That is not ordinary cleverness. That is elite curiosity. Sometimes astronomers also observe the opposite event, when the planet passes behind the star. This is called a secondary eclipse. For a brief time, any light or heat coming from the planet is hidden, leaving only the star's contribution. Compare brightness before, during, and after that disappearance, and you can estimate how much radiation the planet itself was adding. This matters enormously for hot worlds like 55 Cancri, because the planet is likely extremely warm. It emits infrared radiation. In simpler terms, it glows with heat. By measuring changes in infrared light as the planet orbits, scientists can estimate dayside temperatures, nightside contrasts, and heat redistribution. We are in effect reading warmth from across interstellar space. If that sentence feels absurd, good, it should. Some observations of 55 Cancri suggested very high dayside temperatures consistent with molten surfaces. Other data hinted that heat patterns changed over time. Perhaps the hottest region shifted. Perhaps total emission varied. That led to several possibilities: volcanic resurfacing, changing atmosphere, cloud layers of vaporized minerals, moving lava fields, or some combination not yet fully understood. Data does not always arrive with subtitles. Instead, scientists compare competing explanations. Which model best fits the measurements? Which assumptions are reasonable? Which uncertainties dominate? Could instrumental noise mimic a signal? Could stellar activity confuse the interpretation? Could the planet itself be more complex than our first model allowed? This is where science becomes less about dramatic discovery and more about disciplined doubt. 55 Cancri has repeatedly invited that discipline. Now let us talk about the star, because the star is both source of information and source of trouble. To measure planetary signals, astronomers must understand the host star carefully. Stars are not perfect light bulbs. They have spots, flares, granulation, magnetic cycles, and natural variability. If the star brightens or dims slightly on its own, that can imitate or obscure planetary signatures. Imagine trying to hear a whisper while the room itself occasionally coughs. So researchers model stellar behaviour, calibrate instruments, gather long data sets, and compare observations across time. The cleaner the understanding of the star, the clearer the planet emerges. In a sense, planets are often discovered by subtracting stars from stars. This is also why multiple telescopes and methods matter. One observatory may measure transit depths, another may track radial velocity wobble, a space telescope may capture infrared phase curves. Together, different tools cross-check each other. No single clue must carry the whole burden. That collaborative nature of evidence is beautiful. A world no one can touch becomes known through many small agreements among independent measurements. Let us imagine how this looks in practice. A telescope collects photons all night long. Each photon left the 55 Cancri system 41 years ago. Some were emitted by the star, some were reflected or re-radiated after interacting with the planet. They strike detectors as tiny counts of energy. Numbers accumulate, software processes them, curves appear on screens. Researchers search for periodic dips, spectral lines, thermal shifts. There are no cinematic explosions. Mostly there are graphs, yet hidden in those graphs may be lava seas, orbital speed, atmospheric escape, or a world sized to remarkable precision. That should make us kinder to graphs. Now consider uncertainty, because uncertainty is not weakness. It is honesty quantified. A transit depth may have an error bar. Temperature estimates depend on model assumptions. Composition can be degenerate, meaning multiple interiors fit the same mass and radius. Atmospheric interpretations may remain tentative. Scientists publish ranges, probabilities, confidence levels. This can frustrate people who want certainty packaged neatly. But uncertainty is how real knowledge behaves near the frontier. If someone claims total confidence about a world we cannot directly inspect, caution is appropriate. 55 Cancri has changed in interpretation over time precisely because better data arrived. Orbital period estimates were refined. Carbon-rich star measurements were revisited. Atmospheric claims debated. Thermal variability discussed. That is progress, not embarrassment. Reality usually becomes clearer by first becoming more complicated. There is another clue astronomers use: phase curves. As the planet orbits, we may see different fractions of its illuminated hemisphere, somewhat analogous to lunar phases. For a hot exoplanet, brightness changes across the orbit can reveal where heat is concentrated. If the brightest point is directly under the star, circulation may be limited. If it is shifted east or west, winds or magma transport may be moving heat around. Imagine learning about alien weather by noticing which side glows more brightly. That is phase curve science in spirit. For 55 Cancri, such analyses help test whether the planet has a substantial atmosphere, exposed molten surface, or both. A thick atmosphere can move heat. Bare rock behaves differently. Molten regions may shift thermal signatures. No single answer is guaranteed, but each data set narrows the landscape of possibilities. This is the modern art of planetary inference. The planet itself remains silent. We interrogate photons. There is something deeply human about this method. We often understand distant things indirectly. We infer the presence of wind from swaying branches. We infer someone's mood from posture. We infer history from ruins. We infer unseen planets from trembling light. Knowledge does not always require direct contact. Sometimes it requires patient interpretation, and there is comfort in that. Many things in life feel hidden or far away until enough small clues accumulate. Meaning often arrives gradually. Earthly life trains us to trust what is obvious. Astronomy trains us to trust what is subtle. That may be one reason space science feels calming at night. It reminds us that quiet signals matter. A tiny dimming of starlight can reveal a world. A slight heat excess can hint at magma. A repeated timing shift can expose another planet. Small patterns can contain enormous stories. While you rest on a stable world with breathable air and mercifully cool furniture, telescopes continue collecting ancient light from systems like 55 Cancri. Somewhere in that stream of photons are more answers waiting to be extracted by careful minds. Whenever humans discover a new world, one question arrives almost immediately. Could anything live there? We ask it about icy moons, dusty Mars valleys, deep ocean vents, cloud layers of giant planets, rogue worlds drifting in darkness, and now, naturally, a blazing super-Earth likely covered in molten rock. It is one of our most persistent habits. We meet the unfamiliar and wonder whether life has joined us there. That instinct is revealing. It says something kind about our species. We do not only ask what a place contains or how valuable it is, we ask whether it could host life. So let us ask honestly about 55 Cancri E. The short answer, at least for life as we currently understand it, is that this planet appears profoundly inhospitable. Its dayside temperatures may reach levels hot enough to melt rock. It orbits extremely close to its star, receiving intense radiation. It may be tidally locked, creating severe contrasts between hemispheres. Any atmosphere could be unstable, chemically harsh, or unlike anything breathable. Surface conditions likely include molten regions, extreme heat stress, and geological volatility. If Earth is a garden, this is a forge. For familiar biology, that matters immediately. Life on Earth depends on a few broad themes: liquid solvents, stable chemistry, usable energy gradients, molecular structures that can persist long enough to replicate, and environments that are not constantly destroying the very molecules life requires. Water plays a central role here because it is an excellent solvent, abundant and liquid across a useful range of temperatures and pressures. On 55 Cancri E, stable surface liquid water is not a realistic expectation under current conditions. It would be vaporized, dissociated, or absent. Organic molecules exposed openly would struggle against heat and radiation. Proteins, membranes, DNA-like systems, and many known biochemical structures would fail rapidly. That sounds decisive, and for Earth-like life it largely is. Yet science has learned caution when declaring where life cannot exist. Again and again, Earth has expanded our imagination. We once thought life needed sunlight, then discovered ecosystems around deep-sea hydrothermal vents powered by chemistry. We thought freezing environments too harsh, then found microbes in Antarctic ice. We thought acidity prohibitive, then found organisms thriving in acid pools. We thought radiation impossible, then found microbes astonishingly resilient to doses that would horrify most mammals. Extremophiles, organisms adapted to extreme environments, taught us an important lesson. Life is more flexible than our first guesses. So should we leave a tiny door open for 55 Cancri E? Yes, but with honesty about how narrow that door is. The challenge is not merely one extreme factor, it is many at once. High heat alone is difficult, but perhaps not impossible in principle, if sheltered environments exist. Radiation alone can sometimes be managed biologically or physically. Chemical toxicity alone can be adapted to in some systems, but combined searing temperatures, possible magma seas, volatile atmospheric chemistry, tidal locking extremes, and long-term stellar stress, and the problem becomes much harder. Life prefers some continuity. 55 Cancri A appears to specialize in disruption. Still, let us examine possible niches carefully. One place people often imagine life surviving is underground. Subsurface environments can shield against radiation and buffer surface temperature extremes. On Earth, vast microbial communities live beneath the ground in rock pores, aquifers, and deep sediments. Some rely on chemical energy rather than sunlight. Could something analogous exist deep within 55 Cancri E? Perhaps in principle, if there were regions with temperatures and pressures allowing stable complex chemistry. But this is where internal conditions matter. A planet with strong geothermal gradients and high overall heat may remain too hot across large depths near the surface. Deeper still, pressure rises enormously. There may be narrow zones where conditions become comparatively moderate, but we do not know enough to treat them as likely habitats. The idea is not impossible. It is simply speculative in the extreme. Another imagined refuge is the twilight boundary between permanent day and permanent night on a tidally locked planet. On some worlds, the terminator zone could offer milder temperatures than either blazing dayside or frozen nightside. Science fiction loves this concept, and reasonably so. However, 55 Cancri E may be so close to its star and so intensely heated that even this boundary could remain far too hostile for known life. Instead of gentle sunset conditions, one may get merely less catastrophic. That is not the same as habitable. What about the night side? Permanent darkness sounds cooler, and likely is cooler than the day side. But cooler does not necessarily mean friendly. Heat transported through atmosphere, magma circulation, or crustal conduction may still keep temperatures severe. If the atmosphere is thin, nightside chemistry may be unstable. If thick, circulation may drive fierce winds. Darkness alone solves fewer problems than one might hope. There is also time. Life usually benefits from long periods of relative stability. Evolution needs persistence. Ecosystems need continuity. If the surface of 55 Cancri E is geologically active, resurfacing repeatedly, with atmospheric changes or thermal fluctuations over time, then even temporary niches may be fragile. A habitat that appears for a short interval, then disappears into lava is not ideal real estate. Now let us entertain a broader question. Could life use chemistry very different from ours? This is one of the most exciting unknowns in astrobiology. We know only one origin of life, Earth. That means our sample size is one, statistically a humbling number. Perhaps life elsewhere uses solvents other than water. Perhaps silicon or sulfur chemistries play roles under exotic conditions. Perhaps information molecules unlike DNA exist. Scientists remain open to possibilities, but openness is not the same as evidence. Extreme heat poses a deep challenge because many complex molecules become unstable. Information-bearing systems require enough persistence to replicate and evolve. If thermal motion constantly tears structures apart, life struggles to gain traction no matter the chemistry. There may be windows we have not imagined, but heat remains a stern gatekeeper. In that sense, 55 Cancri E may be less a cradle and more a test of chemistry's limits. Could transient airborne particles host microenvironments? Could mineral surfaces catalyze self-organizing reactions? Could deeper pressure-stabilized regions harbor unknown systems? These are interesting theoretical questions. Yet with present evidence, none are favoured explanations. We have no sign of life there, only a fascinatingly extreme planet. And sometimes that is enough. There is another way something can survive on a planet. Not life, but structures. Could human technology survive there briefly? Perhaps robotic probes with heavy shielding, high-temperature materials, active cooling, and carefully planned mission profiles might someday endure for short periods. Engineers already designed systems for Venus-like conditions and industrial furnaces, but 55 Cancri raises the challenge dramatically through distance, heat, radiation, and gravity. Sending a rover there would not be a weekend project. Still, if future civilizations ever deploy such machines, they may become our eyes in places biology cannot go. That thought is comforting. Curiosity can survive where flesh cannot. Now compare this world to Earth for a moment. Here, life occupies forests, oceans, deserts, glaciers, hot springs, caves, city gutters, your kitchen sponge if neglected, and soils rich with invisible ecosystems. Our planet is not merely habitable, it is exuberantly inhabited. Life filled every workable niche it found. That abundance can make us underestimate how rare usable conditions may be. A world like 55 Cancri restores perspective. Planets are common. Friendly planets may be less so. Habitability is not automatic. Breathable air, moderate temperatures, liquid water, protective atmosphere, stable cycles, magnetic shielding, suitable chemistry. These are not background defaults. They are achievements of circumstance. When we ask whether anything could survive there, we are also quietly asking why so much survives here. That is one reason astrobiology is emotionally valuable. It turns outward curiosity into inward gratitude. Now imagine, impossibly again, standing in orbit above 55 Cancri E. Below lies a glowing hemisphere, perhaps molten in places, wrapped in strange gases. You ask whether life could exist there. The answer may be no, at least not now, at least not in forms we know. But the universe loses nothing by containing some worlds that are not homes. Deserts exist, oceans exist, ice exists, volcanoes exist. Sterile worlds may still be beautiful, informative, and necessary parts of cosmic diversity. Not every place must host life to matter. And who knows how many gentler planets orbit elsewhere, unseen tonight, where biology found easier beginnings. 55 Cancri may be a poor candidate for life, but it is an excellent teacher. It teaches us what heat can do, how stars sculpt planets, how atmospheres struggle, how geology persists under punishment, and how narrow the band of comfort may sometimes be. It also teaches humility about our assumptions. For centuries, humans imagined planets as variants of Earth. Then we found hot Jupiters, ocean worlds, tidally locked rocks, planets denser than expected, lighter than expected, stranger than language prepared us for. The galaxy appears less interested in repetition than we hoped. That means life, if common, may also surprise us. So while 55 Cancri itself may not host thriving ecosystems, the broader lesson is hopeful. Nature creates many experiments. Some fail for life. Others may succeed brilliantly. If it seems so extreme today, was it always like this? Or did 55 Cancri once pass through gentler ages before becoming the furnace we infer now? Nothing in the universe is born finished. Stars brighten, cool, and age. Galaxies collide. Moons drift outward. Atmospheres thicken or vanish. Oceans appear, freeze, boil, and sometimes disappear entirely. Mountains rise only to be worn down grain by grain. Even the most solid-looking planet is not a statue. It is a process. That truth matters greatly for 55 Cancri. When we picture this world now, we imagine a close-orbiting super-Earth scorched by its star, possibly wrapped in strange gases, perhaps hosting molten surfaces and deep compressed interiors. But the planet we infer today may not resemble the planet that formed billions of years ago. Worlds have histories, and extreme worlds often have dramatic ones. So let us ask a gentler question than whether it is habitable now. Let us ask what it might have been before it became what it is. Planetary history usually begins in a disk. Around a young star, gas and dust swirl in a flattened rotating cloud. Tiny grains collide and stick. Pebbles become rocks. Rocks become planetesimals. Planetesimals merge into embryos. Some are smashed apart. Some survive. Some gather gas envelopes. Some are flung outward or inward by gravitational encounters. It is less like neat construction and more like long-term celestial improvisation. Somewhere in that busy early disk, the material that became 55 Cancri assembled. Was it born exactly where it is now, hugging its star in a blistering orbit? Possibly. But many astronomers suspect that at least some close-in exoplanets formed farther away and later migrated inward. That possibility makes the story far richer. If 55 Cancri formed at a greater distance, temperatures in the surrounding disk would have been lower. Different minerals could condense. Volatile compounds might survive more easily. Water-bearing material may have been more accessible. Carbon chemistry could differ. The planet's earliest composition might have included ingredients no longer stable near its present furnace-like location. Then gravity rearranges everything. Migration can happen through interactions with leftover gas in the disk, resonances with neighbouring planets, scattering events or long-term orbital evolution. Giant planets elsewhere in the system can disturb smaller ones. Chains of worlds can shuffle inward and outward over time. A stable orbit today may hide a chaotic youth. If 55 Cancri once lived farther out, then its journey inward may have transformed it profoundly. Imagine taking a cold stone from the shade and placing it near a fire. The stone remains the same object, but cracking, heating, chemical alteration, and stress begin immediately. Now enlarge that idea to planetary scale and give it millions of years. As the planet moved closer to the star, surface temperatures would rise. Any shallow water would vanish quickly. Ice would sublimate. Atmospheres rich in light gases might expand and escape. Minerals stable in cooler regions could decompose or melt. Internal temperature structure would shift. Tidal forces from the star would strengthen. A migrating world may carry memories in its composition. There is another possibility. Perhaps 55 Cancri formed close in from the beginning, inside the hot inner disk. In that case, it may have always been a world of refractory materials, substances able to withstand higher temperatures during formation. Iron-rich, rock-rich, volatile poor matter could dominate. The planet might have begun harsh and remained harsh. This scenario is simpler in some ways, but still dynamic. Even a planet born near a star changes dramatically through time. Young stars are often more active than mature stars. They spin faster, flare more strongly, emit intense radiation, and drive powerful stellar winds. If 55 Cancri was more energetic in youth, then early conditions on the planet may have been even more severe than today. Whatever atmosphere existed may have been stripped more aggressively. Surface materials may have melted more extensively. Escape of lighter elements could have reshaped composition. Ironically, the calmer present star may represent a gentler era. This is one of the strange themes of astronomy. Old age in stars can sometimes mean improved manners. Now let us think about atmosphere, because atmospheres are among the most changeable planetary features. Earth's atmosphere today differs greatly from the one our planet had billions of years ago. Oxygen was once scarce. Volcanic gases dominated early periods. Life itself transformed atmospheric chemistry. Mars likely lost much of a thicker ancient atmosphere. Venus may once have had water before greenhouse runaway and solar effects altered everything. So what of 55 Cancri? It may once have possessed a thicker volatile envelope, perhaps hydrogen-rich, steam-rich, carbon-rich, or chemically mixed depending on origin. Over time, intense heat and stellar radiation could strip lighter gases away, leaving a denser remnant atmosphere or only transient outcast layers replenished by volcanism. If true, the sky we imagine now is not original, it is what survived. That phrase has power beyond astronomy. Survival states are common in nature. What remains after billions of years of pressure tells a different story than what existed at the start. The surface may also have changed repeatedly. A world under strong tidal stress and heavier radiation can remain geologically active. Magma may rise, crust may crack, lava plains may spread and cool, only to be remelted or buried later. Impacts in early history could have resurfaced vast regions. Chemical weathering, if any atmosphere allows it, may proceed in unfamiliar ways. Maps there would age badly. On Earth, we often rely on craters to estimate surface ages elsewhere. More craters usually suggest older, less active terrain. Fewer craters can imply resurfacing. For 55 Cancri E, direct surface imaging is beyond us for now, so we infer activity from heat signatures, orbital context, and physical modelling. Yet if lava oceans or major volcanic systems exist, then ancient scars may have been erased many times over. The planet may have rewritten its face repeatedly. Its interior evolves too. Young rocky planets retain substantial heat from formation and impacts. Radioactive elements add more. Over time, interiors cool. Mantle convection slows. Core processes change. Magnetic dynamos may weaken or strengthen depending on structure and timing. Crystallization fronts move. Mineral phases transform as pressure and temperature conditions shift. Inside 55 Cancri E, deep layers may have changed continuously for billions of years while the outside baked. Even if diamond-like carbon phases formed in some interior zones, those zones need not remain static forever. Rising heat, changing pressures, mantle mixing or partial melting may alter distribution over immense timescales. Planets are not layered cakes preserved in refrigerators, they are slow engines. Another intriguing question is whether orbital distance itself changed after the early disk vanished. Multi-planet systems can continue evolving long after formation. Gravitational nudges among planets may shift eccentricities and inclinations. Tiny changes can matter enormously for a close-in world. A slightly more elliptical orbit increases tidal flexing and internal heating. A more circular orbit reduces some extremes. Neighbouring giant planets may have influenced 55 Cancri's path through secular interactions over ages. This means today's lava world may have experienced hotter and cooler chapters, geologically speaking, depending on orbital history. Not cool in the comfortable sense, unfortunately. Could it ever have had liquid water? That depends heavily on where it formed and when it migrated. If born farther out with water-rich material, temporary water-bearing phases are conceivable early on, but once close to the star, long-term surface water stability becomes highly unlikely. Any ancient water may have escaped, reacted into minerals, or vanished into deep reservoirs before a later release. A lost ocean is speculative, but not impossible in planetary history terms. The universe is full of former things, former lakes on Mars, former atmospheres on small worlds, former rings around planets, former stars consumed in mergers, former orbits changed by encounters. 55 Cancria may also be a former something, perhaps a former temperate embryo, former volatile-rich mini-world, former thicker atmosphere planet, former cooler body later dragged inward. Or perhaps it was always a furnace, and the change has been mostly internal rather than climatic. At present, we do not know with certainty, yet uncertainty here is fertile rather than frustrating. It means the planet still has secrets. There is a human tendency to freeze things in their current state. We meet a person and assume they were always like this. We see a landscape and forget glaciers once carved it. We see a planet glowing in hostile orbit and assume it was born glowing. Time is usually more creative than that. Even Earth would look impossible to many moments in its own past. A molten early Earth, a snowball Earth, an oxygen-poor Earth, a dinosaur Earth, a forested coal swamp Earth. Same planet, wildly different chapters. So why not 55 Cancri as well? Learning that planets change over time can also be comforting in an ordinary way. Conditions that seem fixed often are not. Stability may hide motion. Harsh phases may soften. Quiet surfaces may churn below. Present appearances rarely tell the whole story. This distant world, scorched though it may be, is still part of a long unfolding process. Imagine observing it across billions of years in accelerated motion. The young star blazes stronger. The planet migrates or settles. Atmosphere swells, escapes, reforms. Lava sheets spread, crust fractures. Interior cools slowly. Orbital resonances shift. The star ages into steadier maturity. Through it all, one world persists, altered but continuous. That is a grand patience beyond human timescales, and yet we can infer pieces of it from a few decades of data. There is something deeply satisfying about that. A species that struggles to remember where it left charges can still reconstruct the biography of a planet 41 light-years away. Take two worlds made from stardust, add gravity, give them time, and you do not necessarily get similar results. That may be one of the most useful lessons hidden inside planetary science. We sometimes speak of planets as though they belong to one familiar category, as though a world is simply a round place with weather and ground and perhaps some inconvenient politics. But planets are outcomes, not templates. Small changes in distance, mass, chemistry, timing, or neighbouring worlds can produce radically different destinies. Earth and 55 Cancri E illustrate this beautifully. At first glance, there are reasons people compare them. 55 Cancri E is often described as a rocky super-Earth. It is larger than our planet, denser than gas giants, and likely composed substantially of rock and metal. It is not a star, not a Jupiter-like giant, not an icy distant dwarf. In broad family terms, it belongs closer to Earth than many other exoplanets do, and yet in lived experience these worlds may feel almost opposite. Earth orbits one astronomical unit from the Sun, comfortably far enough that water can remain liquid across large surface regions. 55 Cancri circles extremely close to its star, completing a year in less than one Earth day. That difference in orbital distance alone reshapes nearly everything else. On Earth, sunlight warms without sterilizing most surfaces. On 55 Cancri E, stellar radiation likely drives temperatures high enough to melt rock on the day side. We receive seasons. It may receive punishment. Now, consider rotation. Earth spins once every 24 hours, giving us regular cycles of day and night. These cycles shape sleep, weather, temperature balance, ecosystems, and culture. Dawn matters here. Evening matters here. Even language is filled with rotation. Tomorrow, tonight, sunrise, noon, late afternoon, midnight. 55 Cancri is likely tidally locked or near it. One side may face the star continuously, while the other remains in permanent darkness. If so, no global sunrise sweeps across the surface, no familiar night cools the day side. No morning birds complain from trees because trees have wisely declined involvement. That difference alone transforms the meaning of time. Now let us talk about water. Earth's surface is dominated by liquid water oceans. Water moderates climate, stores heat, erodes rock, cycles through clouds and rivers, supports life, and gives the planet much of its appearance from space. The pale blue marble image exists because water participates everywhere. 55 Cancri E may instead host molten rock seas or at least extensive lava regions under extreme heat. If Earth's oceans regulate life, this world's possible magma oceans regulate geology. Both may have oceans. Only one invites swimming. Atmospheres tell another striking story. Earth's atmosphere is nitrogen-rich, oxygen-bearing, pressure-balanced for our biology, and chemically transformed over time by life itself. It shields us from much radiation, allows weather, and keeps temperatures within survivable ranges through a subtle greenhouse effect. The atmosphere of 55 Cancri E, if substantial, may be composed of exotic gases, vaporized rock species, volcanic outgassing products, or layers in constant struggle against stellar stripping. It may glow with heat rather than carry breathable wind. It may change rapidly or remain difficult to characterize. We step outside and inhale automatically. That luxury deserves more respect. Gravity offers a more nuanced comparison. 55 Cancri E is more massive than Earth and likely exerts stronger surface gravity. Walking there, if one could survive, would feel heavier. Muscles would work harder. Jumps would disappoint immediately. Dropped objects would hurry downward with confidence. Earth's gravity, by contrast, is strong enough to hold oceans and air, yet mild enough for trees, birds, stairs, and recreational dancing. It is a balanced setting we rarely praise because we met it at birth. Sometimes normal is merely well-tuned. Now think about interiors. Earth has a metallic core, convecting mantle, plate tectonics, volcanism, and a magnetic field generated by core dynamics. Its interior drives surface change over billions of years. Continents drift, mountains rise, volcanoes release gases. The magnetic field helps shield atmosphere and life from charged particles. 55 Cancri likely also has layered interiors, perhaps a metallic core and high-pressure mantle, but under stronger compression and more extreme external heating. If carbon-rich enough, internal crystal phases such as diamond may exist in some models. Tidal forces from the nearby star may add heating. Earth does not experience comparably. Earth's interior warms the surface subtly. 55 Cancri star may overwhelm everything from above while the inside works overtime below. There is also the question of age and stability. Earth formed about 4.5 billion years ago and has passed through dramatic eras. Magma oceans, heavy bombardment, microbial beginnings, oxygenation, snowball episodes, dinosaurs, mammals, and eventually creatures who misplace charges while discussing cosmology. 55 Cancri may be older than Earth, residing in a mature system that has had billions of years to evolve. It too likely experienced violent youth, migration or orbital changes, resurfacing, atmospheric loss, and deep internal transformation. But its path seems to have remained or become far more thermally extreme. Same universe, different biography. One of the most important comparisons is habitability. Earth is not perfect, but it is profoundly habitable. Liquid water persists, temperatures span workable ranges over vast areas. Chemistry supports life. Energy arrives steadily from the sun. Geological cycling recycles nutrients. Complex ecosystems emerged. 55 Cancri, as currently understood, appears deeply hostile to life as we know it. Extreme heat, possible lava surfaces, harsh radiation environment, uncertain atmosphere, and severe orbital conditions make familiar biology unlikely. This contrast matters because it reveals how narrow the comfortable zone can be. Move too close to a star and oceans vanish. Grow too massive or too small and atmospheric outcomes shift. Alter chemistry, rotation or history, and everything changes. Earth is not inevitable. It is one successful solution among many failed or indifferent possibilities. That realization can feel humbling, but it can also feel comforting. We often treat Earth as ordinary because it is familiar. Yet compared with many known exoplanets, it is astonishingly gentle. Blue skies instead of glowing mineral haze, rain instead of silicate condensation, beaches instead of magma shores, nights cool enough for sleep, gravity suitable for walking the dog. A year long enough that birthdays remain manageable. These are not trivial perks. Now let us compare appearance from space. Earth would show white clouds, blue oceans, brown-green continents, polar ice, shifting storms, and a thin atmosphere hugging the surface. Its brightness varies with weather and seasons. It looks alive because in many ways it is. 55 Cancri might show a bright star-facing hemisphere, intense thermal emission, perhaps molten regions, possible haze, dramatic day-night contrast, and no visible signs of biology. Depending on wavelength, it may be more informative in infrared than visible light. Earth reflects sunlight gracefully. 55 Cancri E may re-radiate absorbed fire. There is also emotional geography. When we imagine Earth, we think of homes, languages, coastlines, forests, roads, family kitchens, city lights at night. A planet becomes personal when inhabited. When we imagine 55 Cancri A, we think of physics, heat budgets, orbital mechanics, mineral phases. Atmospheric escape. It remains impersonal not because it lacks wonder, but because it likely lacks life, and yet it still matters deeply. By comparing it with Earth, we sharpen our understanding of both worlds. Earth teaches us what habitability can become. 55 Cancri teaches us how quickly habitability can be lost or never achieved. Earth shows equilibrium. 55 Cancri shows extremes. Earth offers life-rich complexity. 55 Cancri offers physics-rich complexity. Both are valuable classrooms. There is another subtle comparison worth making: detectability. If alien astronomers around 55 Cancri look toward our solar system, Earth might seem modest in size but potentially interesting due to atmospheric signatures like oxygen and methane together. To them, our world could appear as strange as theirs appears to us. This perspective is healthy. Every civilization, if any exist elsewhere, likely calls its own baseline normal until astronomy corrects them too. Now imagine placing the two planets side by side in a grand educational display. One world with clouds, rivers, forests, and moonlit tides. Another with possible lava seas, a star looming overhead, and a year shorter than our workday. One tuned for biology, one tuned for material science, one where people debate weekend plans, one where rocks debate phase transitions, same cosmos, same laws, astonishingly different outcomes. This is why exoplanets fascinate so many people. They expand possibility space. They remind us that our local example, however beloved, is not the standard model of every world, and they quietly improve gratitude. Fresh water in a glass, air at room temperature, pavement cool enough for shoes, trees that photosynthesize politely, sleep under darkness rather than perpetual noon, a stable chair under moderate gravity. These become more precious when compared with alternatives. First impressions matter, though on 55 Cancri E they might also be your last. We have spent time discussing temperatures, gravity, orbital speed, lava seas, possible mineral skies, and a star that hangs far too close for comfort. Numbers are useful, but numbers can remain abstract. So let us do what humans always do when faced with a distant place. If we could somehow travel there safely, what would we actually see standing on its surface, or what passes for one? Let us imagine arriving there. This requires, of course, impossible technology, exceptional shielding, a spacecraft designed by patient geniuses, and a legal waiver of extraordinary length. We are not making practical plans tonight. We are borrowing imagination to translate science into sensation. Because planets become memorable when they feel real. Picture the approach first. From space, 55 Cancri may not resemble the soft blue worlds that decorate science fiction posters. Depending on wavelength and viewing angle, you might see a bright hemisphere facing the star, darkened contrasts elsewhere, and signs of intense thermal emission. The planet would look less like a calm destination and more like an active process. The star dominates nearby space. It appears large, brilliant, and close enough to make your instincts uncomfortable. Even before landing, you would sense that this world lives under relentless energy. As your craft descends, if an atmosphere exists in meaningful quantity, the upper layers may shimmer with haze, strange particles, or glowing heat signatures. There would be no familiar white clouds drifting over blue, no scattered birds, no weather fronts shaped like home. Any clouds might be mineral-rich, vapor-derived, or chemically exotic. The colours could be bronze, amber, grey, red, or tones no travel brochure has practiced. Already Earth would feel like a very fortunate memory. Now the gravity announces itself. The moment you stand or attempt to, you would feel heavier than home. Legs must work harder. Every movement asks more effort. Raising an arm becomes noticeable. Turning your body feels slower. The suit itself, despite powered assistance, seems to have developed opinions. Gravity is subtle on Earth because we are calibrated to it. Increase it significantly, and ordinary motion becomes labour. You would understand stairs in a whole new emotional way. Then comes the heat. Not the pleasant heat of sunlight on skin. Not even the aggressive heat of desert noon. This would be environmental heat so extreme that survival depends entirely on your equipment. The ground may radiate upward. The air, if present, may carry furnace warmth. Nearby surfaces could glow or remain hot enough to destroy exposed materials quickly. Human senses are not designed to interpret such temperatures directly, because direct exposure would be brief and educational. Your suit systems would hum constantly, pumping coolant, protecting electronics, preventing your visit from becoming a cautionary paragraph in engineering manuals. Look outward. If you landed on the day side, the star might appear fixed in the sky, or nearly so, depending on local orbital dynamics. It would not travel in the comforting arc we know on Earth. No afternoon drift towards sunset, no promise of evening. It simply hangs there, immense and bright, a permanent command to remain hot. Psychologically, that may be one of the strangest sensations. Humans use the sun as a clock. Morning means beginning. Evening means slowing down. Night means rest. On a tidally locked world, one side may lose that rhythm entirely. The sky no longer tells time, it only tells pressure. Shadows would be sharp and uncompromising. If the atmosphere were thin, edges of light and dark might look stark. If thicker and hazy, brightness could diffuse through glowing particulate air. Either way, the scene would feel more industrial than pastoral. Now listen, if the atmosphere is dense enough, you might hear winds moving across rock, distant cracking crust, venting gases, low rumbles from shifting terrain, perhaps the hiss of a hot particle settling. If the air is thin, sound would be muted and strange. Your own suit systems might become louder than the world itself. Imagine standing somewhere so alien that your breathing machinery sounds more familiar than the landscape. Underfoot, the terrain could vary dramatically. Some areas might be hardened lava plains, dark and fractured like basalt fields on Earth, but hotter and more active. Other regions may show crustal plates floating atop molten layers, cracked surfaces revealing brighter material beneath, or slopes glazed by repeated flows. Walking would require caution not only because of terrain, but because the terrain may be younger than your breakfast. There is a common Earth habit of trusting ground. We assume the floor beneath us has committed to remaining floor. On 55 Cancri, that confidence would weaken quickly. Suppose you approached a lava basin. Instead of a water-reflecting sky, molten material might reflect the star in trembling orange-white streaks. Slow swells move through viscous liquid stone. Thin skins of cooled crust form, wrinkle, fracture, and sink. Gas bubbles rise and burst. The shoreline shifts unpredictably. Heat distortion dances in the air above it. You would not be tempted to dip a toe, and yet visually it might be mesmerizing. Dangerous things often are. Now consider smell, at least hypothetically. Your suit would prevent direct exposure, but if chemistry could be sampled safely, the environment might resemble volcanic gases, hot minerals, metal oxides, sulfurous compounds, scorched dust, and reactive species no candle company would market. Earth smells alive. Soil after rain, pine forests, sea air, fresh bread. This place might smell geological. There is also scale. Because the planet is larger than Earth, the horizon may sit differently, the landscape broader. If atmospheric haze blurs distance, mountains or ridges could emerge as dark silhouettes through glowing air. If gravity suppresses very tall topography, scenes may favour expansive plains, ridged uplands, and vast basins over towering alpine drama. A planet chooses aesthetics through physics. Now let us imagine visiting the boundary between day and night, the permanent twilight zone if tidal locking holds. This may be the most compelling place psychologically. In one direction, a burning hemisphere. In the other, endless darkness. Along the horizon, the star hangs low but never sets. Light stretches sideways forever. Temperatures may be less extreme than the day side, though still severe by earthly standards. Standing there would feel like living on the edge of two worlds stitched together badly. Walk toward the light, and heat intensifies. Walk toward darkness, and the sky fills with stars while the planet's own warmth still lingers through rock and atmosphere. Few landscapes in imagination offer such immediate contrast. Now step fully onto the night side. The star never rises here. The sky could be black and crowded with stars, perhaps crossed by hazes or strange clouds depending on atmospheric circulation. If molten regions glow in the distance, horizons may pulse dim red. Winds transporting heat from the day side could move continuously. Temperatures might still be far above anything pleasant, or at least wildly inhospitable. Darkness, it turns out, does not guarantee comfort. This is another good cosmic lesson. Shade solves less than we think when the whole system is overheating. How would your body feel after an hour? Heavy, worked, alert, slightly strained by gravity even with assistance, mind sharpened by danger and wonder, movements deliberate, every step conscious. You would probably miss chairs, trees, breathable air, and weather that does not threaten machinery. Homesickness can arrive quickly when home is exceptional. There is one more sensation worth mentioning: silence of life. On Earth, even empty places are often full of subtle biology. Insects hum, leaves rustle, birds call, microbes scent the air, grass grows, water hosts unseen motion. Life makes background texture. On 55 Cancri, that texture may be absent. No ecosystems layering countless tiny signals into the environment. Only physics, chemistry, wind, heat, and stone. Some people would find that eerie. Others would find it majestic. Both reactions are fair. Yet even there, wonder would be abundant. You would stand on a real world around another star. Every rock beneath your boots formed in an alien system. The light overhead began in a sun not ours. The horizon belongs to a place humanity once knew only as a wobble in starlight. That emotional weight might exceed the physical one. Many astronauts describe Earth from orbit as fragile and precious. Visiting 55 Cancri E, even briefly, would likely intensify that feeling enormously. You would return with fierce gratitude for oceans, breezes, and moderate afternoons. the trip would be less about conquering a world and more about understanding what a gift Earth is. And perhaps that is true of many journeys. We travel outward, partly to come home wiser. Sometimes the most important thing a planet offers is not comfort, beauty, or the possibility of life. Sometimes it offers correction. For a long time, humanity knew only one planetary system well, our own. We had Mercury, Venus, Earth, Mars, the giant outer worlds, moons in abundance, asteroids, comets, and a tidy enough arrangement to make textbooks feel confident. Rocky planets lived inside. Gas giants lived farther out. Ice worlds lingered beyond. Distances seemed sensible. Categories felt clean. Then we began finding planets elsewhere. Almost immediately, the universe started disagreeing with our assumptions. Hot Jupiters appeared where giant planets should not have been, at least according to older expectations. Mini-Neptunes showed up in numbers despite being absent from our local neighbourhood. Super-Earths turned out to be common, even though our solar system has none. Systems packed tightly with multiple planets emerged. Eccentric orbits, resonances, strange densities, and atmospheric extremes became ordinary headlines in astronomy. 55 Cancri belongs to that corrective era. It teaches us first that our solar system is one example, not a template. This may sound obvious now, but it is a profound shift in perspective. Before exoplanets, theories of planet formation were constrained by a sample size of 1. Imagine trying to understand all forests after visiting only a single park. You would learn something real, but you might mistake local quirks for universal law. That was us with planets. 55 Cancri e, a close-in super-Earth likely scorched enough to host molten surfaces, reminds us that rocky worlds need not resemble Earth, Mars, or Mercury in any comfortable way. The same basic ingredients, rock, metal, gravity, time, can produce outcomes we never saw nearby. The universe is not repetitive, it is generative. Another lesson this planet offers concerns habitability. We often ask whether a world could host life, and that is a worthy question. But 55 Cancri teaches the equal importance of asking why some worlds cannot. Extreme heat, intense radiation, orbital locking, possible atmospheric erosion, and severe geophysical conditions show how narrow the window for familiar life may sometimes be. Earth's balance is not guaranteed by the concept of planethood. A world can be rocky and still inhospitable. It can be similar in size category, yet utterly different in experience. It can orbit a sun-like star and still become a furnace. These comparisons sharpen our understanding of what makes habitable planets special. In that sense, hostile worlds help us appreciate friendly ones. This planet also teaches us humility about labels. When 55 Cancri gained fame as a diamond planet, the phrase captured attention instantly. But the deeper scientific story was more nuanced. Mass, radius, density, stellar chemistry, internal models, pressure phases, uncertainty ranges, revised measurements. Headlines prefer sparkle. Reality prefers complexity. That pattern extends far beyond astronomy. Simple names are useful doorways, but they are poor substitutes for understanding. Diamond Planet is memorable. Potentially carbon-influenced super-Earth with debated composition and extreme irradiation is clumsy but closer to truth. Nature often resists our branding efforts. 55 Cancri reminds us that wonder survives complexity. In fact, it often improves. There is another lesson hidden in how we discovered it. No human eye looked at the sky and saw a tiny lava world directly. We inferred its existence from stellar wobble, transits, spectral data, thermal signatures, repeated measurements, and statistical analysis. We learned about a planet through consequences rather than direct contact. This is a triumph of indirect reasoning. Many of humanity's greatest discoveries arrive this way. We infer black holes from surrounding motions. We infer atoms from experiments long before imaging them. We infer dark matter from gravitational behaviour. We infer ancient climates from ice cores and sediments. We infer exoplanets from trembling starlight. 55 Cancri teaches that reality often reveals itself through subtle traces. That lesson is intellectually powerful and personally useful. Not everything important is obvious at first glance. The planet also expands our sense of geological possibility. On Earth, oceans mean water, clouds mean vapour from water, rain means water returning from sky to ground. Rock is mostly solid beneath our feet. These assumptions are practical here, but not universal. Elsewhere, rock may flow like liquid, clouds may contain metals or minerals, atmospheres may derive from vaporized crust, and surfaces may cycle through molten states. The periodic table allows many climates. 55 Cancri tells us geology is broader than terrestrial habit. This matters because planetary science is in part comparative geology on a cosmic scale. By studying extreme worlds, we test our models of heat transport, mantle dynamics, atmospheric escape, tidal locking, and mineral physics under conditions impossible to reproduce fully on Earth. A lava world can teach us about our own planet's distant past. Early Earth likely passed through magma ocean phases after giant impacts and during energetic youth. By observing hot rocky exoplanets today, we may glimpse processes our world experienced billions of years ago and has long since forgotten on the surface. So 55 Cancri may be alien, yet also ancestral in some respects. That is a lovely paradox. The strange can illuminate the familiar. This planet also teaches us patience with uncertainty. Scientific understanding of 55 Cancri has evolved over time. Orbital interpretations were refined, composition debates shifted, atmospheric possibilities remain open, thermal variability sparked competing explanations. New telescopes will likely revise more. Some people find changing answers unsettling. Science sees them as progress. A model updated by better evidence is not failure. It is growth. A universe this complex will not surrender truth in one dramatic moment. It yields gradually to persistence. 55 Cancri rewards that persistence. There is a sociological lesson too. Why did so many people care about a distant, inhospitable world? Because it was strange. Because it was nicknamed. Because it stretched imagination. Because humans are drawn to the improbable. This tells us something encouraging. Curiosity is easier to awaken than cynicism suggests. Give people a planet with lava seas and possible diamonds, and many will listen long enough to learn about orbital mechanics, spectroscopy, density, and stellar chemistry. Wonder can be an educational gateway. That is no small thing. Now let us widen the frame further. The Milky Way likely contains hundreds of billions of stars. Many host planets. Some host several. If even a small fraction possess diverse rocky worlds, then galaxies are filled with environments stranger than our fiction once managed. Some worlds may have global oceans deeper than any trench. Some may be airless iron spheres. Some may orbit red dwarfs under crimson skies. Some may be temperate and quiet. Some may be like 55 Cancri, too close, too hot, too dramatic to ignore. The universe appears not merely large, but inventive. And where there is variety, there is possibility. Not every possibility is hospitable. Not every possibility is beautiful in a human sense, but abundance itself is meaningful. It means our local arrangement is not the only way matter can organize into worlds. That realization can be freeing. Many worries shrink when placed beside cosmic scale, but scale alone is not the comfort. Variety is. The universe contains countless experiments running at once. Failure in one place does not imply failure everywhere. Harshness in one system does not erase gentleness elsewhere. 55 Cancri may be hostile, but it exists alongside worlds we have not yet found. There is also gratitude hidden here. Studying an extreme planet often sends the mind back home. Air at room temperature, water that remains liquid, nights cool enough for sleep, a star at a healthy distance, seasons that challenge but usually do not annihilate, soil capable of gardens, gravity calibrated for walking rather than endurance contests. Earth can seem ordinary until compared with alternatives. A diamond rumour and lava reality 41 light-years away can make tap water feel luxurious. One more lesson deserves mention. Curiosity itself scales. We are a species of finite lifespan living on a small planet, yet we can detect worlds around distant stars, estimate their densities, debate their atmospheres, and imagine standing on their surfaces. We can know things no ancestor could have guessed were knowable. That should inspire confidence in careful thought. The same mind that worries about tomorrow's errands is also capable collectively of understanding planets it will never touch. Human attention is often underused. 55 Cancri E, then, is not only an object in space, it is evidence about us. It shows that we seek patterns, we build instruments, we revise beliefs, we follow faint signals across decades, we turn tiny dips in starlight into planetary stories. That is a noble habit. Now, after travelling so far in thought, it is time to come home. We have crossed 41 light-years without leaving a chair. We have stood beside imagined lava oceans, beneath a sky that may glow instead of breathe, under the stare of a star that never seems to look away. We have felt heavier gravity, watched years pass in less than a day, and listened for clues hidden inside tiny changes of distant light. And yet, for all the strangeness of 55 Cancri Ye, perhaps the most meaningful part of this journey is not what we found there. It is what we notice here, because comparison is a quiet teacher. When we study a world where rock may melt into seas, our own oceans seem gentler. When we imagine an atmosphere made from vaporized minerals, the next easy breath feels more valuable. When we picture a sky with no sunset, evening on Earth becomes something worth noticing again. When we consider gravity heavy enough to burden each step, an ordinary walk across the room becomes a kind of luxury. Sometimes the fastest way to appreciate home is to visit somewhere that cannot be home at all. Earth is not perfect. It has storms, droughts, earthquakes, winters that overstay their welcome, summers that show off, insects with excessive confidence, and many human complications we continue inventing for ourselves. But even with all of that, it remains a remarkably kind arrangement. Liquid water gathers in rivers instead of glowing in lava basins. Clouds carry rain instead of mineral ash. Trees rise from soil rather than crusts of cooling magma. Night arrives softly, morning returns reliably. The floor beneath you is cool enough to trust. There is something deeply comforting in those ordinary facts. We often think wonder must be far away. Another star, another galaxy, another impossible world. But wonder can also be local and overlooked. A glass of water, wind through an open window, the smell of rain, a room held at gentle temperature by thin walls and quiet effort. The ability to rest because gravity, atmosphere, chemistry, and distance from our star all happen to cooperate. That cooperation is extraordinary. 55 Cancri I reminds us that planets do not owe anyone comfort. The universe makes many kinds of worlds. Some burn, some freeze, some choke under thick atmospheres, some wander dark between stars, some may host conditions stranger than we have words for. And one of them, at least for now, hosts you. That may be the rarest detail in tonight's story. Right now, while that distant planet circles its star in another hurried year, Earth continues its slower rhythm. Oceans move under the moon, clouds travel over sleeping cities, forests breathe in darkness, mountains cool after sunlight, countless windows glow, then go dark one by one. Somewhere outside, if your sky is clear enough, stars are waiting. One of them belongs to the system we visited tonight. Its light left decades ago, crossed the dark patiently, and arrived here just in time to be noticed. There is tenderness in that timing. The universe sends old light to present minds, and present minds, even tired ones, can receive it. If your day has been long, let it be long no longer. You do not need to solve anything tonight. You do not need to be as productive as stars, as resilient as planets, or as consistent as orbital mechanics. You're allowed to be quiet. You're allowed to rest. The cosmos will continue without supervision. 55 Cancri E will keep circling. Its hot side will keep facing the star. Possible lava will continue doing whatever lava does on worlds no one has visited. Scientists will keep gathering photons and turning them into understanding, and you, for this moment, can simply breathe the air of a calmer planet. Notice that breath. In, out. No volcanic gas. No mineral haze. No furnace winds. Just the atmosphere of Earth, entering and leaving with ancient simplicity. Let your shoulders soften. Let your jaw unclench. Let the thoughts still trying to work late realize the office is closed. There will be time tomorrow for plans, messages, errands, and unfinished lists. Tonight belongs to slower things, to darkness arriving properly, to blankets, pillows, quiet rooms, and the gentle privilege of being warm without overheating. Perhaps that is one final lesson from distant planets. Extremes are dramatic, but balance is what lets life sleep. If you can hear a faint sound around you now, the hum of a room, distant traffic, wind outside, soft fabric moving as you settle, those are the sounds of a world that supports ordinary life so well we forget it is doing so. There is no need to remember everything from tonight's journey. You do not need to retain mass estimates, orbital periods, thermal models, or the chemistry of speculative skies. Knowledge can drift loosely now. Keep only the feeling if you like. The feeling that reality is larger than routine. The feeling that home is more precious when contrasted with elsewhere. The feeling that even a tired day can end beneath a universe full of astonishing things. Soon sleep may come the same way astronomy often does, gradually, quietly, through signals too subtle to notice at first. If it does, let it. And if you are still awake, then stay here a little longer in the calm. Somewhere beyond sight, 55 Cancri rushes around its star in another rapid year. Somewhere nearer, Earth turns steadily toward another dawn. And somewhere exactly right, in the small space where you are now, rest is allowed. Thank you for travelling with me tonight. Until next time, this has been Science for Sleep. Good night.